Rosand has been around for over 65 years, and we've evolved with the mining industry. So I wish my memory was as good as some of the veterans in our industry. So I'm going to refer to my notes as I explain to you what our service offering is. And if you have any questions or comments, please feel free to drop them in the chat box and I'll address them in the chat box afterwards. So thanks. Rosand provides safe, fast, efficient, and cost-effective drilling and grouting services to mining and exploration industries throughout Africa. For over 65 years, we've applied advanced design and engineering disciplines to create client-specific solutions. Our state-of-the-art in-house manufacturing facilities provide products designed and engineered to meet our clients' specific demands, while our experienced team of engineers and artisans ensure solution in keeping with global best practice. So our organization expands across surface and underground drilling operations. In our underground operations, we do underground drilling with smaller drilling rigs. We also do pack grouting, which provides grout support to areas that have been blasted out from under the mine. I'm going to focus in this instance on our surface drilling operations, where we have seen a lot of growth and a lot of innovation and development in the past 2 years. We have a fleet of over 50 combined old and new generation surface drilling rigs spread across 2 contract sites in South Africa, and on these contracts we employ over 400 people. We currently have surface drilling exploration contracts with major mining houses such as Anglo American's Kumba Iron Ore, Anglo Platinum, De Beers, and Debswana in Botswana. And we've serviced most of South Africa's blue chip mining houses, expanding our operations over our several decades of existence. Rosand has positioned our business for the future, using technology to improve operational effectiveness and find alternative solutions for our clients. In making this shift and transforming digitally, the application of integrated discipline project management and continuous innovations in our technology give us the leading edge in the industry, known for its generally slow uptake in technology. Our surface drilling operations contribute significantly to our company's operations, and these consist of diamond core drilling, percussion drilling, RC, and grade control, and Mr. Colin Rice can teach you a lot about all these different methods. Each type of drilling serves a particular purpose for Rosand's mining clients, such as greenfield exploration to discover new deposits, brownfields projects to augment existing life of mines. Grade control drilling, on the other hand, aims to acquire new geological information and metallurgical information to inform current mining activities. Rosand's machines for each drilling type are standard and interchangeable in terms of platforms, engines, and spare parts. And our in-house Rocal brand of machine has been in existence for decades and undergone operational and safety improvements over time. And now it is being replaced by new gen drill rigs with automated rod handling systems, remote operator cabins, and telemetry systems to record critical data while drilling. The benefit is that our new rigs contribute to improved safety, while data from telemetry systems is used to improve operational efficiencies, to better understand machine capability, as well as being useful for value-added geoscientific and mining analyses and decision-making by the client. On our machines, the in-hole telemetry sensors record big data sets in real time. And this is as close as it gets compared to with how oil and gas industries acquire and handle similar data in real time. An important part of Rosand's mandate is employee development as well, which is critical to ensure that required performance levels are maintained. Here we have training and skills development translated into a personal development plan, which is key to close any performance gaps. For example, each of our operators is subjected to formal OEM accredited training, proficiency grading, and certification to operate just that drill machine. And this is a big journey, considering we have a variety of drill machines, which each person needs specific training for each one. Operator proficiency is enhanced further by on-the-job practical training, and any potential for leadership ability is identified. And this is part of our career pathing as well. So it's not just about our machines, it's about our people and where they're headed in the drilling world. And you may have seen in the news recently, our new technology machines have enabled women to form part of drilling crews. So we believe it's an African first. On our surface exploration contracts, we now have women part of our drilling crew. So we're very proud of that. We're proud of the technology. We're proud of where we're going. We're proud to work with our clients, and we're proud of where our journey is going in terms of digital development. And that is what I have to say about Rosand. So please do follow us on LinkedIn.
Okay, guys, we've got a chunk to get through today. First of all, thanks everyone for joining, and congratulations to Tanya and her team for putting together the most amazing collection of people. It's absolutely incredible the numbers of people that have registered for this course, and well done to you. It's an incredible service to the exploration industry, and well done. And we look forward to doing this for many, many more years. Guys, what I'm going to try and talk to you about today in a very, very short period of time is to give you an idea of what we believe a geologist needs to know about drilling. And this is really, really hard to do this in a very short period of time. So I've kind of condensed things, a little bit of technical stuff, a little bit of philosophical stuff, if you like. And we're going to try and get through this. Now, just as Chelsea was chatting there, I could see on the screen the people who have joined this course, and I see some people who are not new geologists. They are well-practiced geologists, people I've worked with for many, many years. So I hope they've come to maybe refresh their memories, possibly. But I'm going to keep this presentation fairly fundamental from the point of view of the depth that we're going into. And I'm going to assume that we're all newish geos. I must preface all of this by saying that I'm not a geologist. I used to be a maths teacher back in the good old days. But I'm not a geologist, but I do work a lot with geos. So what I want to do is to try and give you an outline of what I believe, based on my years of experience and the work that I do with mining companies and exploration contractors, an idea of what I believe you need to know about drilling, so that as you move through your careers, you develop your career as a geologist, you maybe focus on these issues that I will highlight. So just to start off with, we know that all geological information is founded on rocks, whether it's a chip or a core sample, it's all founded on rocks. And so we have to drill holes in the Earth's surface, and thank goodness we do, else we wouldn't have work. So drilling is a critically important part of a geologist's life, and a deep understanding of drilling is, I believe, is a core competence of every geologist. And a great deal of the work that I'm involved in is involved in solving problems which really stem from misunderstandings between geos and contractors. And very often, geos don't understand how a contractor works, and even more often, contractors don't understand what a geologist wants. And so you have these conflicts, and very often I get involved in trying to sort those conflicts out. We must all understand that drilling is a complex operation. It involves high-powered machinery, and there's been a massive shift in maybe the last 7 or 8 years, maybe even less, for mining companies to move away from the old mechanical, manual type of drill rigs to automated drill rigs. And while this is great, it's fantastic, we must never lose sight of the fact that these machines cost significant amounts of money. They don't suit every drilling operation. Greenfields, remotes, in jungle operations, on mountaintops, it's very, very hard to get this equipment in there. So we must be very, very aware that a lot of the new developments that are taking place, while they are fantastic, they improve safety, they improve productivity, we must understand that they're not universally applicable in all exploration projects. So we can get from different methods of drilling. We're going to talk about drilling methods in a minute. I just want to try and set the scene of what we're trying to do in this period this morning. There are many, many, many different methods of drilling and many different techniques of drilling. I'll explain to you just now the difference between the two. And basically these techniques, these different methods and techniques will produce either a chip sample or a core sample. And the geo needs to determine, obviously, before you start drilling, whether you want a chip sample or a core sample. And they will fit into different stages of the exploration project. In early stage exploration projects, a chip sample would be fine. It will be adequate for what we want to do. But in later stage projects, we have to have core samples. And so it'll move into a much more expensive, much more lengthy, much more complex core drilling exercise. So what do you need to know about this? What does a geo need to know about? And this summary is based on the work I've done over many, many years working with geos and mining companies. I believe the first thing a geo needs to know is you need to have a good understanding of different methods of drilling. You need to understand what the method can do, and more importantly, what it can't do. Frequently, I come across situations where geo has in his head that you can drill from here to Australia in 2.5 days. Well, you can't. And we have this misunderstanding. Very often, let's be fair, sometimes it comes from contractors promising more than they can deliver. But you need to have a good understanding of different methods of drilling, what they can do and what they can't do. What they can't do is sometimes the most important part. Then the next most important thing I think a geo needs to understand are the factors that affect the representativity and the quality of samples that you produce. Drilling is expensive, irrespective of the method of drilling. It's expensive, and you drill to get a quality, a sample of the best quality that you possibly can. And very often there are many, many factors that affect the quality of that sample. And representativity. I'll just very, very quickly talk about what I believe representativity means. Representativity's got two components to it. It means that the sample we get is truly representative of the in situ rock that we've drilled. And number two, that it comes from a known depth. That word depth is very important in exploration drilling. And I can tell you right now that based on many years of working in the industry, very often hole depths are misreported. Very often. And one of the key things a geo needs to understand is how you measure the depth of a borehole. And if you don't, we can chat about it later. I haven't included it in this little presentation. So we need to understand the factors that affect the quality of the samples you get, because very often I see geos get delivered samples that are of poor quality. There's ground core, there's mixed chip samples, there's inaccurate RC sampling. So you need to understand that because you need to control the quality of what you get given. Then third, many people argue this is should be the first thing in the list. You have to have a very good understanding of safety aspects of drilling. In South Africa, a geologist has a very significant safety responsibility. In other parts of the world, they don't. I was chatting to some guys. So can somebody turn their mic off there, please, guys? I was doing a little course for some guys in Canada recently, and this particular company, their geos didn't have a great safety responsibility at all. But just your duty of care says that you need to have a good understanding of safety aspects of drilling. So that's another aspect. That involves your legal responsibilities and liability as well. In South Africa, it's very well defined. We've got very defined legislation. I'm not going to talk about it today because we've got people from all over the world in this course. But you need to know your legal responsibilities and your legal liability. What happens if you drop the ball? What happens if you do something that injures someone or God forbid, causes a fatality? And then the fifth thing that I think you need to know is you need to understand the factors that affect the cost of drilling. You need to understand how a contractor makes money. And I'm going to talk a little bit later. I'm going to have to, hopefully we'll get to the last parts of this course today. The geo has a very, very big impact on whether the contractor can or cannot make money. And let me say something here that we'll talk about as we go through. We'll repeat it a few more times. A contractor has to make money. He has to make money. And I often say to geos, part of your job is to make sure that he makes money. If he's a poor contractor, he should not have gotten the work in the first place. And that's not his fault, that's your fault. he should never have gotten the work. But if he's a good contractor, he must make money, he must make a profit, and you must do whatever you can to assist him to make a profit. And that might sound a little bit offbeat, but I promise you it's true, and I'll explain in some more detail later. So I believe geos need to know about these things, and if you then analyze them, I think we can break it down into three categories of knowledge, if you like: technical, safety, and economic. And I'm going to try and get through all of this today. Okay. As I said, I believe that a successful exploration project will flow from a clear understanding, where the geo and the contractor are in sync, where they understand each other's requirements. I think we have the makings of a good contract. So the first thing I want to talk about here quickly, I'm going to rush through this, guys. Well, not rush through it, but we've got a lot to get through, and I'm going to go through this hopefully quickly enough that we can get to the end of today. Geologists must understand some fundamentals of drilling. They must understand how different drilling methods work. And one of the most fundamental things, and I come across this, oddly enough, very, very often in drilling operations, where even experienced people don't understand these basic fundamentals. Every drilling operation, every method of drilling that you will ever come across anywhere in the world in your entire life will involve a drill bit that is put in contact with a rock and a drill string. And the drill string is made up of drill rods, or lengths of what we call drill pipe. They are typically 3 or 6 or 9 or 12 meters in length. In the oil and gas industry, they're even longer, but typically in our industry, they're 3 or 6 meters long. And the bit is put in contact with the rock, it is rotated, and at the same time, we put load on the bit, we push down onto that drill bit, and the drill bit fractures the rock. And the pure function, the only function of the drill bit is to cause the rock to fragment, to cause rock failure. And that happens in different ways that we might get around to talking about just now. And the purpose of the drill string is it provides rotation, it provides torque to the bit, it allows you to put weight on the bit, allows you to push down and put load on the bit. And also something very, very critically important is all drill strings are hollow. It's tube, so it's got a hole in the middle. And through the tube, through the drill string, we pump a drilling fluid. And that drilling fluid flows down the drill string, past the face of the bit, and up the side of the borehole, what we call the annulus. That is the space between the borehole wall and the drill string. And the purpose of that drilling fluid is to remove the drilled cuttings, the chips that we create, the fragmented rock from the borehole. And every single drilling method involves those basic principles. If you're drilling a hole in the wall to hang a picture up, or drilling a hole in a piece of wood, or drilling a 4-kilometer deep hole to explore for gold, those same fundamental principles apply. And all that varies really, guys, is the nature of the drill bit and the drill rods that we put on. And we will select a drill bit according to the purpose of our drilling project. So if you look, for example, here, let me try and get my little laser pointer here. I think this will work. This bit on the left-hand side is what's called a tricone bit. Widely used in oil and gas exploration, very widely used in drilling blast holes on open cast mines, in surface mines. And this drill bit, as you can see, it's what we call a full face drill bit. So when this bit drills, the entire volume of rock is fragmented. And so we call that a full hole drill bit. The bit on the right is a polycrystalline diamond drill bit, also a full face drill bit, widely used in oil and gas exploration and production holes. Again, it's a full hole bit. So the entire borehole becomes chip sample. This bit at the top in the middle is what we call a drag bit, the one on the right. We also call that a drag bit. It's got 3 wings on it, three legs, if you like. And in this particular case, it's got tungsten carbide cutting elements. We call that a drag bit. And then this bit at the bottom, it's got a hole in the middle, and that's a diamond core bit. So in this type of drill bit, this part here where you can see these natural diamonds on what we call the kerf of the bit, the circular part, the cutting part of the bit, if you like. The central part becomes core, and it's only that part where the diamonds are that becomes cutting. So all that varies really in different methods of drilling is the type of drill bit that we use. And we'll talk about this one just now. So let's look at what I consider to be the most fundamental, the most important part of understanding drilling methods. In every drilling method, guys, anywhere in the world, wherever you drill, whatever you drill, you have to have rotation of the cutting elements. It's the most fundamental feature of every drilling operation. So we put the bit in contact with the rock and we rotate it. The speed of rotation varies according to the bit and various other factors, but in every drilling operation, we have to rotate the drill bit. So rotation is one of the key elements. And there's different ways. There's different types of drill rig that provide that rotation in different ways. We're not going to go into that now, but there are different types of methods or different mechanisms, if you like, for imparting that rotation to the drill bit. Then the second essential feature that is common to every method of drilling is thrust, or weight on bit or bit load. All of these things, they mean the same thing, and I tend to use them interchangeably. We cannot just put the bit in contact with the rock and rotate it. We need to put load on the bit. We've got to push down onto the bit so that there is some pressure between the cutting elements and the rock face that we are drilling. And we call that bit weight or bit thrust or bit load. And it's very important. Again, different types of drill bit will require different levels of bit load. And we need to understand what those different levels of bit load are. The third feature that is common to every drilling operation is what we call a bit weight control system. Sometimes when we drill, the rock is extremely hard. We've got to push hard. Sometimes it's softer, and we've got to push with less weight. And the drill rig has got to have the ability to alter that weight on bit. If we can't alter the weight on bit, we're going to damage the bit, we're going to cause deflection in the hole and all sorts of other problems that we won't talk about now. But we have to have this, what we call a bit weight control system. Then the fourth system, the fourth essential element of every drilling operation is a hoisting system. At some point in time, the drill bit is going to be finished. We're going to have to pull it out the hole, change the bit, put a new bit on, and go back into the hole and continue drilling. And that can happen multiple times in the life of a borehole. We might have to hoist for other reasons as well. But we have to have the drill rig, our drilling operation has got to have the ability to pull and lower what we call rod tripping. It's got to be able to trip drill rods, pull and lower drill rods. It's a critical feature of every drilling operation, every drilling method. We've got to have the ability to hoist. And that function is provided by the drill rig. And many, many mining companies believe that that drill rig hoisting is the most dangerous part of a drilling operation. It's not, but we tend to think it is. And so we push very, very hard for rod handling systems. Rod handling systems where you remove human beings from the operation, and the operation is done mechanically. They're fantastic, wonderful, huge strides in reducing manual labor, but it is not the most dangerous operation on a drill rig, not by far. But we think it is, but we'll talk about that later. So when we pull rods out the hole, when we trip the drill rods, we pull them out either as what we call singles or multiples or stands. So if we, for example, are drilling with 3-meter drill rods, I could either pull my rods out 3 meters at a time, or if my drill rig allows it, I can pull out 6 meters at a time. In other words, 2 rods at a time, what we call a stand. And typically, we would stack these drill rods horizontally, either on a rod sloop, a trailer of some sort, a rod carrier, or we'll stack them on racks like this. Now, fortunately for us, we don't do this anymore. And again, this is one of the problems that we frequently see, and geologists, by your training, should be able to multiply. One of the things in the drilling industry, people can't multiply, and so we don't understand the mass of the steel that we put out of a hole. This rig here, for example, on the left-hand side, this was a rig in South Africa a while ago, a number of years ago. I went to do an audit at, and these guys were drilling this drill pipe that you can see here. This is what's called BQ drill rod. It weighs 6 kilograms per meter. And this hole was 1,650 meters deep, 1,650 times 6. is about 10 tons roughly. So about 10 tons, 10,000 kilograms of steel laying on these little rod racks that you see here. And nobody batted an eyelid. Nobody thought anything about it. Nobody realized how much weight there was. Now, 10 tons, a small, medium-sized car weighs about 1.5 tons. That's about 6 or 7 cars sitting on those little rod racks. I don't think I would do that. I don't think I'd put that much weight on those rod racks. So in the old days, when I first started in the industry, we did not lay rods horizontally. We stacked them vertically in the mast. Now, there's many reasons why we don't do that now, but it's essentially in South Africa, it's banned. We're not allowed to do that. And again, we're not going to go into this in any detail, but I can tell you right now, if you want to afterwards, I'll sit down, I'll explain it to you. Stacking rods horizontally is much more dangerous than stacking them vertically. People think that stacking rods vertically, like you see in the right-hand side here, is dangerous. If it's done properly, it's not. But because we drill many angled holes, we can't stack in the mast and so on. So we stack rods horizontally. But these are safety issues that geos need to understand, safety and productivity issues. And we can't go into all the detail now, but please bear that in mind. The fifth, the last of the essential features of every drilling operation is a flushing system. In every drilling operation, we fragment rock. This bit down at the bottom, whichever type of bit it is, doesn't matter, it fragments rock. It creates what we call drilled cutting. Guys, please don't call it sludge. It's drilled cutting. It's rock that we've drilled. And we've got to get those rock chips. They vary in size, but we've got to get those rock chips out the hole. So we pump down the middle of the drill string, we pump a flushing medium, a drilling fluid. It's either air or water. Let me rephrase that. It's either air-based or water-based. And we pump that drilling fluid down the drill string. It flows past the face of the bit, picks up the cutting, and then transports the cutting to surface. And that is an incredibly important part of the whole operation. And I'll tell you right now that as a geo, you're going to come across in-hole problems. You maybe are already on projects you work on. And I can tell you 95% of the problems, the in-hole problems that occur in drilling operations occur because of poor hole cleaning, because people don't understand how much cutting we generate when we drill a borehole and how important it is that that cutting comes out. And we'll talk a little bit about that in a slide or two. So we drill either with water or with air. If we drill with water, we will have a sump. We will have reservoirs of some type. They'll either be earthen sumps, in other words, holes dug in the ground, or they'll be above ground sumps. There'll be tanks or some sort of a reticulation system above ground. But the principle's the same. We'll have a circulation pump, a positive displacement pump. We'll suck drilling fluid out of the reservoir. We'll deliver it down the drill string. It flows past the bit and up the annulus to surface. If it's a water-based system, we'll generally recycle that. So it'll flow through a series of troughs and sumps to help settle the cutting out. It'll then flow back into that main sump where it's then recycled. So we have this recycle system. If we're drilling with air, we don't have a water pump, we have an air pump, which we call a compressor. And the compressor sucks atmospheric air into it, it compresses it, and then delivers that high pressure air down the drill string. And in this case, exactly the same thing happens, but with air, the air blows the cutting to surface. It can't carry it. It's got no carrying capacity, so it blows the cutting to surface. And so that leads us to two very important differences. If we're drilling with a drilling fluid that is water-based, we talk about what we call the annular velocity. And that is the velocity of the fluid, the speed of the fluid as it flows up the annulus. In other words, from the bit to the collar, to surface. And typically, we want the annular velocity to be between 30 and 50 meters per minute, roughly in that range. If it's too low, if our velocity is below 30, we have a danger of not being able to clear the cutting quickly enough. We might not get all the cutting out the hole. If the annular velocity is too high, then the fluid flowing up the side of the borehole becomes erosive, and it can cause hole enlargement. I'll talk about that in a minute. That is the biggest problem and probably the cause of 95% of in-hole problems, this hole enlargement, because we've got the wrong angular velocity, our pump rate is wrong, and so we cause this hole enlargement, what we call washouts. If we're drilling with air, air's got no carrying capacity, so now we need a much higher velocity. And I won't talk about this now, but when we talk about air, we talk about what we call an upper hole velocity. So we want a much higher speed in order to get the cuttings out of the hole. It's going to blow the cutting out the hole. I can't get into this, but if anybody comes on the longer courses we do, either the drilling methods and techniques course we do for the Geological Society, or any of our certificate programs that we offer, I talk a great deal about the flushing system. It is without a question the most important part of a drilling operation, and without a doubt the most poorly understood amongst contractors and geologists. Why is this so important? Very quickly, let's put one little slide in here just to illustrate what I'm getting at. If you look at the picture on the left, whether we're drilling with air or water, it doesn't matter. If my hole is engaged, in other words, it's the same diameter or very close to the same diameter from the bottom to the collar, then the angular velocity will be constant from bottom to top. It shouldn't vary. If, however, I've got a washout, if the hole is enlarged for some reason, that might be a water-sensitive zone, it might have been a caving zone, whatever the case. But if the hole is enlarged, then from the bit up to the, sorry, I'm trying to get my mouse to work. Then from the bit face up to the start of the washout, my angular velocity will be perfect. But as the fluid enters the washed out zone, the volume of that zone increases, and so therefore my velocity will reduce. And the velocity in this washed out zone will be reduced. And the cutting that we have evacuated, that we've taken up to that point, literally is in suspension. It sits there in the borehole until we switch the pump off for whatever reason, and that cutting then falls back to bottom. Borehole enlargement is a huge problem, and please, I want you to try to remember that. The last little bit of basic I want to talk about here before we start talking about some more technical stuff. Some people say that geos sometimes don't understand too carefully. I want to just 2 minutes talk about how we design a borehole. When we design a borehole, we have a target depth that we want to get to, and we will drill a bigger diameter through the top weathered section of the hole, what we call the overburden. So we'll drill a largest diameter through there, and I've tried to show you that in my very, very good PowerPoint picture here. We'll then pull that bit and drill string out, and I will run in the second picture a string of casing. Casing is nothing more than a tube, a steel tube or PVC tube, depends upon the depth and the purpose of the hole. And the purpose of that casing is purely and simply to maintain the integrity of the top of the hole, to stop the hole caving in and causing problems. I will then take a smaller size bit with a smaller size drill string, and I'll then advance through the bottom of the casing. And I will continue my hole, hopefully to target depth, but sometimes I will hit a geological issue. It might be caving ground, it might be a water-sensitive zone, it might be a great big circulation loss, but I will reach something that is going to prevent me advancing the borehole, or it's going to dramatically increase the risk of completing the borehole. And so what I might do then is we might have to run another string of casing. So in other words, I pull that drill string out and I run another string of steel casing, steel tubing in to case off that problematic zone that we've seen. I will then have to take a smaller drill string, a smaller bit and smaller drill string, and then drill through that second string of casing. And this is essentially how we design boreholes. The principle here is this, guys, is we always design boreholes from the bottom up. So as a geo, based on the nature of what you're looking for and your assay or testing techniques, you will have a certain minimum core size, a certain minimum sample size that you want at target depth at the bottom of the hole. And so you will, based on your knowledge of the lithology, your knowledge of the potential risks in the hole, you'll say, okay, we need 1 casing string or 2 casing strings. So we don't need a casing string at all. And so you'll design the hole from bottom up. So that's important for you to remember as well. Okay. All right. So we've got 5 essential elements. And guys, if you remember this, you've made a good start to understanding how a drilling operation works. So when you look at a drilling operation, you go to any operation, whether it's an RC operation, surface, underground, diamond drilling, blast hole drilling, it doesn't matter. Look at that operation and ask yourselves, how do we get rotation? How do they put thrust on the bit? How do they control the weight on the bit? How do they hoist draw rods, and what type of flushing system are they using in this operation? It's only 5 things you need to understand. If you understand those about a drilling operation, it will help you to understand a lot more the more complex issues that come up. Okay, very quickly, very quickly. The next bit of fundamental knowledge you need to have is we need to understand how different bits make hole. Every drilling operation involves fragmenting rock. We've got to fragment rock. And the more quickly, the more efficiently we can fragment that rock, the more quickly we can drill. And so we have just a rough understanding. This is quite complex. I'm going to rush through this quite quickly. There are 3 mechanical ways that we can make rock fail. We can crush rock, we can shear rock, and we can abrade rock. We can make rock fail chemically, but we don't use that in drilling applications. So we've got 3 mechanical ways that we can make rock fail. Let's look at each of them in turn. The first way is we can crush rock. So we take something like a bit like we saw earlier, what we call a tricone bit. This one obviously upside down. We put it in contact with a formation. We put huge amounts of load in it. This is a big full face bit. Because it's a full face bit, we've got to put a huge amount of load on it. We've got to push down with a lot of force, and we simultaneously rotate the bit. And these little cutting elements you see here, these are tungsten carbide teeth. And those teeth literally penetrate the formation. They cause the formation to crack and spall and for a cutting to develop. And as the bit rotates, those teeth constantly create new cracks and new cutting. But it's a crushing action. And we know that this bit will not make whole, it cannot cause failure of the rock unless the load we apply exceeds the compressive strength of the rock. So the greater the compressive strength of the rock, the higher the load we need, the greater the weight on bit we need to make these bits cut. I'm going to come back to that later. The second way that we can make rock fail is we can shear it. So if you take a bit like I've got on the right here, what we call a drag bit, you might remember that from earlier. We've got 3 wings on this bit. You can't see the third one, it's stuck at the back there. We put this in contact with the rock and we rotate it. And the cutting elements slide across the rock face, very similar to a knife sliding through butter, and you get the shearing action. It's not a crushing action, it's a shearing action. So it's a slightly different type of cutting action in this case. And these blades, the cutting elements, the stuff that does the work, it can be steel, it can be tungsten carbide, it can be polycrystalline diamond, it can be a number of different cutting elements depending upon the type of rock that you are cutting. And then the third way that we can make rock fail is we can abrade rock. And this is the cutting action, the cutting mechanism that a diamond bit uses. And on the left-hand side there, you've got what we call an impregnated diamond bit, where the diamonds in that cutting structure are synthetic diamonds that looks like yellow sugar, made in a factory, synthetic diamond. The bit on the right, these diamonds here are natural diamonds mined in a diamond mine and then set into a bit body. But these cutting elements are relatively small, and they cut in a similar way to sandpaper or emery paper. So they rely on the rotational speed. They rotate very, very fast so that those small cutting elements can abrade away the rock. So we drill here with very high rotational speed, but very low weight on bit. Because they're diamonds, we don't want big weight because we're going to cause the diamonds to fracture and we lose our cutting ability. So it's a high speed, low weight type of cutting action. And so you can see then a diamond bit with very, very fine cutting elements lends itself to drilling hard rock. And so we use diamonds in core bits. And hopefully you're going to get core a little bit more like the one on the left rather than the one on the right. And so if we summarize this quickly, we've got three mechanisms to make rock break. We can crush it, we can shear it, we can abrade it. And as long as you've got a basic understanding of that, you will then be able to understand how different methods of drilling work. We can't spend too much more time on that, unfortunately. Okay, so let's get down to the nitty-gritty. Let's get down to the more important part of what I want to chat today. We've got an understanding. We know that there's 5 essential elements in every single drilling method you will ever come across anywhere in your life. And there are 3 ways that we can make rock break. Now, one of the things that I find most frustrating, in fact, probably the most frustrating thing that I've come across in the 36 years I've been working in the drilling industry, is we call things different names, and it causes massive confusion. For example, I was talking to some Australian guys the other day, and they talk about air drilling. Well, when you talk about air drilling, it means, to me, it means you've got a compressor, you're flushing with air. And I can use air to flush many different drilling in many different drilling methods. So it doesn't, I know what they mean. In South Africa, we talk about percussion drilling. We talk about RC drilling. Those terms are wrong. And I get a bit pedantic about it, a bit like an old person, but there's very good reason for it. So I believe one of the key things that geos need to understand, one of the key things we must all agree on, is a nomenclature, a naming system, a classification of drilling methods. And I've got a very simple method here. And if you can remember this is great. It'll help us to maybe when we talk about things, we know exactly what we're talking about. We can classify the left-hand side here, there are these 4 blocks. I believe the best way to classify methods of drilling is to classify them by the rock breaking mechanism. So we've got pure percussion methods of drilling. We're not going to talk about them, but we've got pure percussion methods of drilling, where the bit is made purely to hammer. There's no rotation, it's purely a hammering action. And the bit penetrates the rock, creates chips, and so we make holes. So we've got pure percussion methods of drilling. Then we've got pure rotary methods of drilling. Diamond drilling, where we drill with a core bit, is a rotary drilling method. There's no percussion, there's no hammering action. It's a pure rotary drilling method. Then we've got a combination of the two. We've got what we call rotary percussion methods, where we have both the percussive action and rotation of the drill bit. So those 3 basic things there cover all of the methods of drilling that we commonly come across. So if you take, for example, rotary drilling, I'm not going to talk about percussion, guys. We'll just leave that out for the time being. Okay. When we're at rotary drilling, for example, I can distinguish 2 different techniques of rotary drilling. Rotary drilling is a method, but there's 2 different techniques. I can use a full face bit, a tricone bit or a drag bit, and I would call that full hole rotary drilling. Then we've got diamond core drilling, where we use a different type of bit, a bit with a hole in the middle, a core bit. They're both rotary drilling methods, but they are different techniques. We've got different equipment, we've got different weight on bit, we've got different drill rods, we might have different flushing systems, but they are rotary drilling methods. Similarly, we've got different rotary percussion methods. We've got rotary percussion methods where we have a drill string with a bit at the bottom, and the percussive action happens at the top of the drill string. So we've got a hammer that hammers at the top, the energy wave is transferred through the drill string into the bit crushes rock, and then we flush the chips to surface. Or we have what's called a downhole hammer technique. We're at the bottom of the hole, just above the bit, we've got a hammer, and that hammer hammers the bit. And then we've got another rotary percussion technique, which is very, very important to us, what is commonly called RC in the excavation industry. It's not RC drilling, it's called dual tube RC drilling. I'll explain that to you just now. So the point I'm trying to make here, guys, is we've got defined methods of drilling, and we have got different techniques. So it's the method that's slightly altered, if that makes sense to you. Okay, so I want you to please bear that in mind as we go through this. All right. Okay, so let's look at a couple of these methods. I'm not going to go into massive detail because we're going to run out of time, and I'm looking at my clock very, very carefully here. I want to just talk about these just in rough, broad terms, okay, just so you get an idea of how the method works, the principles of operation, and to some extent what the capabilities of each of these methods are. So let's look quickly. Let's start with rotary percussion drilling, and we'll end up with diamond drilling. Okay, as we said here, there's two main kinds of rotary percussion drilling. This is where we've got both rotation and a hammering action, a percussive action. We've got what we call top hole hammer and down hole hammer. So we've got two systems here. Either we have a drill string with a bit at the bottom. Let me get my little pointer back. We've got a drill string with a bit at the bottom, and the hammering action takes place at the top of the borehole. I'm not going to explain how that happens now. It's beyond what we're talking about today. But we make the hammering action at the top, and the energy wave, it travels through the drill string into the bit. The second way is what we call a downhole hammer system, where the hammering action takes place at the bottom of the hole. So we can have a 300-meter deep hole, but the hammering action still takes place at the bottom. Obviously, the energy transfer in a downhole hammer is more efficient than in the top hole hammer, and so it has certain advantages and disadvantages. We can't go into that in too much detail now. But this downhole hammer, the system that I've spoken about on the left, it's a pneumatic system. So we blow high pressure compressed air through the drill string. The drill string enters the hammer, that bottom part of the drill string, and essentially that high pressure compressed air causes a piston to reciprocate. And I've got it shown schematically here on the right-hand side. So that piston moves up and down very, very fast, very, very high frequency. Anything from 900 to 1200 blows per minute. So very, very high frequency. And every time it comes down, it hits the drill bit, transfers an energy wave through the bit. The buttons of the bit penetrate the rock, cause the rock to fracture. The air then blows the cutting past the bit and back up to surface. That's the basic principle of a downhole hammer. It is a pneumatic tool, so therefore it relies on high pressure compressed air. And the higher the pressure of the air, the more efficient this hammer will be in drilling. Okay. There are many different sizes, diameters of downhole hammer, many different designs. There's dozens of manufacturers of downhole hammers around the world. They all have different designs, different things in the inside of them. But the important thing for you to remember, guys, is that there's only two parts really that are important: the bit and the piston. All this other stuff that you see here, this is just one example of a hammer. All of the other stuff, all that does is it makes the piston reciprocate. That's all it does. So the principles of every downhole hammer are the same. High pressure compressed air, piston that reciprocates, strikes a bit. The same air that makes the piston work escapes at the bit and blows the cutting to surface. They all work in exactly the same way. We won't talk about that now. Very quickly, the main working part, or one of the key main working parts of a downhole hammer, are the drill bits. And drill bits vary in design. These little buttons that we see here, these are tungsten carbide buttons. We can vary the diameter of the button. We can vary the shape of the button. We can vary how they are arranged on the bit face. There's all sorts of variations that can take place to suit a particular drilling condition, to suit either a hardness or an abrasiveness of a particular rock. And we certainly won't go into that. And as a geo, you want to stay well clear of this. You leave this kind of stuff to the contractor to understand. Okay, I'm not going to talk too much about that because we're going to run out of time. I want to talk now quickly about the next. You will all agree, I'm sure, that if we're using a downhole hammer, the air going down the drill pipe, you see I've got it blue here because it's clean air, if that makes sense. It enters the hammer, the piston reciprocates, strikes the bit crushes the rock, and the rock is then blown up the annulus, the rock chips. You will all agree with me that that sample, those chips, are contaminated samples. In other words, they've moved up from the bottom of the hole to the collar of the hole, and they could have picked up contaminants as they moved up the annulus. So a downhole hammer produces a contaminated sample. Now, downhole hammers are very efficient drilling tools. They drill hard rock very efficiently. But they produce this contaminated sample. So geos wanted an uncontaminated sample produced very quickly from hard rock conditions. And way back in Canada, I believe it was like the early 1950s, a long, long time ago. In fact, oddly enough, that's when I was born, a very long time ago. The Canadians developed this dual tube system, what we commonly call RC. It was a system that was developed to drill very soft coal formations. They couldn't core drill, it was too soft and friable. And somebody came up with this dual tube system. And the concept was like this, guys. You have, instead of having your drill string in one piece, it's in two pieces. So you've got an outer tube and an inner tube. And the concept was this. They arranged that they blew compressed air down between the two tubes. The air traveled down. It then it exited just above the drill bit. I'll show you a picture just now. There was a little hole, a little outlet just above the drill bit. The air then flowed out of that annular space, around the face of the bit, picked up the cutting, and then blew the cutting to surface up the inner tube. It was a system developed in Canada to drill these soft coal formations. And so the bit they had at the bottom was a little drag bit, just like we saw just now, a little tungsten carbide drag bit. And it worked extremely well. It was incredibly efficient. And they got these fantastic samples that they couldn't get in any other way. And they said, that's fantastic. They then took that same technique and they tried to apply it to hard rock, to harder formation. But this silly little drill bit here couldn't drill hard rock. And so they said, it doesn't work, and they put it on the shelf. And then, as the story goes, in the early 1970s, the Aussies, who are probably the best RC drillers in the world, they make the best equipment. Most of the best RC equipment comes out of Aussie, or certainly a large part of the good equipment comes out of Aussie. They sort of picked up this technique and they further developed it. And Geo said, look, we want to use this technique because it gives us an uncontaminated sample. The sample coming up the inner tube is not contaminated by anything in the annulus. The air going down is not contaminated. And so it was a great high-speed, relatively inexpensive sampling method. But Geo said, we want to drill hard rock. We don't want to use these tricone bits and drag bits because the penetration rate is too slow. And so they then started to develop face sampling hammers, reverse circulation hammers. It works in exactly the same way as a downhole hammer we spoke about earlier, but it allows the sample to flow the other way. So what we have, and I've shown you here, this is a particular a picture I took from an Atlas Copco brochure, but it shows the principle very well. You have your dual wall drill pipe. So you've got your drill rods with the inner tube, and then that inner tube extends into the hammer. So this tube here that you see is called a sample tube. And in this picture, it shows you it's almost the same length as the hammer. And so the way that this hammer works is that the air comes down between the two tubes, it enters the hammer, the piston reciprocates, strikes the bit creates a chip. The air then escapes out just above the bit here, in these little holes that you see just above the bit. The air travels across the bit face, picks up the cutting, and blows the cutting up through the sample tube, through the inner tube to surface. So it looks like this. I'll come back to the pictures just now. So we have our hammer down the bottom. We've got our dual wall drill pipe. The air comes into what we call a side entry swivel. It's don't worry about that too much, but the air is allowed to enter the annular space between the two tubes. It travels down the two tubes. It enters the hammer. The piston reciprocates. The air then escapes just above the top of the bit, flows across the bit, and the cutting flows up through the sample tube, through the inner tube, through the head, into what we call a sample hose, into a sample collecting system. But the key point here, 2 key points. It's a pneumatic system. It's a downhole hammer system. So I can drill hard rock incredibly quickly, very, very fast. And then the second thing is I get an uncontaminated sample. And that's the key to what we call an RC system. I get very pedantic about it. I call it a dual tube RC system, because the system is based on having the dual tubes, on having the inner and the outer tube. So we get this uncontaminated sample produced. Now, one of the keys to dual tube reverse circulation drilling is collection of the sample. We must always bear in mind, very often we forget this. We are drilling RC, we're drilling dual tube reverse circulation to produce a sample, not to make a hole in the ground. It's to produce a sample. And very, very often what happens is we have this beautiful hammer, we've got a beautiful drill rig, and we get the sample to surface and then we turn it into rubbish because we handle it incorrectly. We mix it, we contaminate it, we spill it, we bag it incorrectly, we label it incorrectly. And so the sampling of that, of a dual tube reverse circulation sample is critical. One of the other important things we must remember is that when we drill an RC hole, a dual tube RC hole, typically it's about, it varies, but 114 to sort of like 150 millimeters in diameter. So we produce this big bulk of sample. We produce between 30 and 45 kilograms of cutting per meter. Now, we're not going to send 30 to 45 kgs of cutting to an assay lab to get assayed. So we want to produce what we call a split sample, a smaller representative sample. And so we use either a riffle type splitter, which are pretty much out of favor now, or what's called a cone splitter, either a fixed cone or a rotary cone splitter. I'm not going to go into all the detail of how these things work because we're going to run out of time, but we have a splitter that takes that bulk sample and then splits it so we get a much smaller sample that is representative of that bulk sample. And in that word representative, there's a whole debate. I have seen really good reverse circulation operations. I've seen really bad reverse circulation operations where basically you're wasting your time because of the sampling process, because of the way the samples are bagged and handled and so on. So we must not forget that the purpose of this is to get a sample, not to drill a hole. It's to get a sample, and we must consider every aspect of this operation from the time the sample enters the sampler until it gets to the lab where the assays are going to be done on it. Okay, all right. I'm not going to talk about this, guys, because we're going to run out of time. I want to just quickly make sure we all understand this flow of air. So the air flows, we're looking now up a hammer up to the top of the borehole, if you like. So the air flows down the drill string into the hammer. The piston reciprocates, the bit strikes the rock face, creates chips. The air escapes in these little ports here, these little holes here between this black ring, if you like, what's called a shroud. It comes down, picks up the cutting, and the cutting evacuates into these holes and then back up the inner tube. So that's the way that the the sample flows. So these two holes are actually, they're sampling holes. That's where the sample enters. Okay. All right. So those are our two roach percussion methods of drilling, two roach percussion techniques, downhole hammer and dual tube reverse circulation. Please, if we meet in the field one day and I ask you what you're doing, if you say you're doing RC drilling, I'll be less than happy. You're doing dual tube RC drilling. Okay. All right. Let's move on to the next one. Let's talk about rotary drilling methods now. I'm not going to talk about full hole rotary drilling. We're talking about exploration drilling. So I'm going to talk about diamond core drilling. And this gets a little bit detailed in places just now, but we have to get into a little bit of detail here, unfortunately, guys. Okay. Let's get into talking about diamond core drilling. In a diamond core drilling operation, the bottommost part of our drill string, the front, sitting behind the drill bit, is what we call a core barrel. And I'll try to show it here in this, my little PowerPoint picture here. So we've got our diamond bit at the bottom here, which I've shown in sort of goldy color because we've got diamond in there. It's got a hole in the middle, and sitting behind it, we have a what we call a core barrel. And we'll talk a lot about core barrels just now. And this core barrel will be a certain length. Let's assume that it is 3 meters in length. So the principle is we will have the bit on bottom. We'll start rotating and we'll start feeding, and we will advance the borehole the length of the core barrel. So this core barrel will now be full of core. It will then be necessary, we can't advance any further, it'll then be necessary to pull the drill string out of the borehole. We pull the entire drill string out the hole, pull all the rods, we hoist them out the hole, remove the bit, take the core out, pack the core into core boxes, into a core box, reassemble the bit, go back to bottom, and when we're on bottom, we'll again start rotating and feeding, and we'll again fill up the core barrel. So the point here is we advance the borehole in stages equal to the length of the core barrel. And so we advance the length of a core barrel in each run. Now, if the core barrel is 3 meters long, in theory, you're going to advance 3 meters, pull and lower, advance 3 meters, pull and lower, advance 3 meters, pull and lower. We call that a conventional system, where the core barrel has to be pulled out of the hole in order to extract the core sample from it. It's a method of drilling, it's a method of retrieving core that we still commonly use in the exploration industry, but we've got other methods we'll talk about just now. But what the important thing is this, is that sometimes I can't drill the full 3 meters. Sometimes I can only advance less than a full core barrel. And so I'll advance in shorter lengths depending upon the nature of the formation and other factors. So let's look at diamond core drilling operations. We've got different kinds of drill rig, and we're not going to go into these in detail, but one of the most common types of diamond core drill rig that you will see around is what we call a hydraulic long stroke drill rig. And these are 2 examples here of long stroke drill rigs. The one on the left is set up for a vertical hole, and the one on the right set up for an angled borehole. The second type of drill rig that we have is what's called a top drive drill rig. And this is a picture of a top drive rig here. We're not going to go into this in any detail because it's just way too complicated for this stage. We need a much longer time to talk about these rigs in detail. But all I want you to know is that there's different types of diamond core drilling machine that we have available. Now, one of the key things that confuse geologists, I want to just spend 2 minutes talking about this. One of the key parts of the diamond drilling industry that confuses people is the naming system that we have. Diamond core drilling had its origins in North America, in Canada and the United States, way back. And in Canada and the United States, they worked in inches and feet. They worked in, it wasn't in the, it was in imperial units of measure, not in metric units of measure. So their bit sizes were in inches. And they named they standardized their bit sizes, the borehole sizes, and they designated them by letters. And so we designate diamond drill hole sizes by letters. So we have E, A, B, N, H, and P hole sizes. If you've been working in the drilling industry, you will have come across these terms. So if I talk about a B size borehole, a BQ hole or a BX hole or a BXM hole, it's a 60 millimeter, nominally 60 millimeters. It's actually 59.96, but it's nominally 60 millimeters in diameter. An N size borehole is 76. So if we here, for example, if we say this is an NQ drill bit, as soon as we see the term N, we know it's designed to drill a 76 millimeter borehole. If I say this is an NQ drill rod, I know that that drill rod is designed to drill an N-size hole. It's obviously not 76 in diameter, it's a bit smaller, it's 70 millimeters in diameter. But the key point here is we use letters to designate hole sizes. And what you as exploration geos will come across in most parts of the world are these three terms here, N, H, and P. A P-size hole is 122, an H-size hole is 96, and an N-size hole is 76. If you're drilling underground, you might come across A and B sizes, A and B size equipment. This will all make a little bit of sense a little bit later, I hope. So that's the one key thing in the diamond drilling industry, is we designate hole sizes by letters. If you work in Europe, they use metric sizes. And so they don't use the same terminology. So you get basically sort of North American designations, and you get metric designations. So you get North America, you get imperial designations, and you get SI units or metric unit designations. Gets very complicated, so we'll leave that. We'll leave that there. So let's look at the most important part now. Forget about the drill rigs and the drill rods, all the rest of it. The key part of a diamond drilling operation from a geologist's point of view is the core barrel, that bottommost part, the part that the core feeds into when you're drilling. It is the most important part, and it acts as the receptacle for the core. That's where the core feeds as the bit advances. And the core barrel, there are many, 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 many different designs of core barrel, many different sizes of core barrel, and they are all designed, I was going to say for different rock types, that's nonsense, but we can use them in different applications depending upon what we are trying to do. But the important thing for the geo to understand is that the core barrel will determine the diameter of your borehole, NH, B, or P. It will determine to a large extent, it'll certainly determine the core size that you get, and to a very large extent, it will determine the quality of the core sample you get, and that will become clear as we move on now. So this little picture here at the bottom here is a picture of a whole bunch of different drill bits, and these are all bits for different designs of core barrel. So these two here, for example, it's hard for you to see, but maybe you can get an idea from your screens there. These are both 60 millimeter bits. These are both B size bits, 60 millimeter bits. The one on the right is what's called a BQ bit. The one on the left is called a TBW bit. You can see the core sample from this core barrel is very much bigger than the core sample from the BQ bit. So it's a different design of core barrel, gives us different diameters of core sample. These three bits here are N-size bits. They are 76 millimeter bits. And again, you can see they've all got different core sizes. They're all 76 OD, the outside diameter is 76. This one on the right is called an NQ bit. This one on the left is called a CUD 76. We won't even worry talking about that. And this one is called a TNW. So you can see the curve, the cutting area changes, so we get different sizes of core. And then finally, these two bits are both H-size bits, both till 96 millimeter holes. And again, you get different core sizes from these bits. Okay, let's look at different designs of core barrel. I want to talk quickly now about different types of core barrel. Now, we've got different ways that we can core drill holes. And the way I explained just now, a couple of minutes ago, we have our core barrel, we advance the hole, the core barrel is full of core. I need to pull the core barrel out the hole. I've got to hoist the entire drill string out the hole, remove the core from the core barrel, reassemble it, and go back into the hole to continue drilling. We call that a conventional system. And I want to quickly show you here different types of conventional core barrel. Many of you will never be involved in conventional drilling. You will use what we call a wireline system that I'll talk about just now. But the principles here are important because it will explain to you how we can affect core quality using different types of different types of core barrel. There are three types of conventional core barrel that we can use, what we call single tube, double tube, and triple tube. In a single tube core barrel, very simply, let me see if I can get my little pointer back here. In a single tube core barrel, we have at the bottom, we have a bit and a reaming shell. In every core barrel, we have a bit and a reaming shell. Then I have an outer tube and I have the core barrel head. So I have one tube. So as we're advancing, as we're drilling, the core's feeding into this single outer tube, hence the name single tube core barrel. The disadvantage of a single tube core barrel, again, is one of my very, very high quality PowerPoint pictures. I hope you can make this out, guys. In a single tube core barrel, I'm pumping my drilling fluid, the water-based drilling fluid, down the drill string. It enters the core barrel. And because the core is sitting inside the tube, the fluid has to flow over the core, past the bit, back up to surface, back up the annulus to surface. So the drilling fluid has to flow over the core to get through the core barrel and back up to surface. So obviously, if the core is at all friable or washable, it's going to merely wash it away. So we use single tube core barrels, either where we've got really hard rock that is going to be immune to any water washing, or in cases where we don't really care about core quality. For example, in that top overburden in the weathered section, we might use a single tube core barrel to drill that. We don't really worry about the quality of the core in that area, and so we might use a single tube core barrel there. The second kind of core barrel that we use, second type of conventional core barrel, is called a double tube core barrel. Now in this core barrel, we've again got our bit and reaming shell. We've again got an outer tube. We've again got a core barrel head, just like we had before. But the difference here is that we've now got an inner tube that is connected to the core barrel head. And it's hard to see in this picture now, but as we drill, the core doesn't feed into the outer tube, it feeds into the inner tube. And the drilling fluid flows through the drill string, through a series of holes. Now, I've shown you a blow-up picture here. In the core barrel head, there's a series of holes drilled through the head. So the fluid flows down the drill string, through these holes. It then flows down past the inner tube on its way to the bit and out to the annulus. So the core, because the core is housed inside the double tube, inside the inner tube, I beg your pardon, it is protected from water washing. So a double tube core barrel will give us a much better quality of sample than a single tube core barrel will. Obviously, it's more expensive, it's more difficult to make, and the costs of drilling with a double tube core barrel will be significantly higher than drilling with a single tube core barrel. But all I want to illustrate here, guys, is how we can get a more sophisticated core barrel and we can get a much better core sample. And that's important for a geo to understand. One other quick thing I want to talk about here, in this core barrel head, where it's connected to the outer tube, I beg your pardon, to the inner tube, we have a set of bearings. And those bearings allow the inner tube to remain stationary while the outer tube and the bit and the drill string are rotating. If the inner tube rotated, it would tend to twist the core with it, and you would get an element of core grinding taking place. You'd get damage to the core. So these bearings are very important. They keep the inner tube stationary while you are drilling. Okay. Now, sometimes, this is very important, guys. Sometimes the process of removing the core sample from the inner tube, because when we retrieve the core barrel to surface, the sample is sitting here inside the inner tube. And sometimes, this is important to understand this distinction, the process of removing that sample destroys the sample. The core is so fractured or broken or friable that the process of removing it, getting it into the core tray, destroys it, and I can no longer see any features in it. And so in those cases, we use what we call a triple tube core barrel. So basically, it's a double tube core barrel, but inside the inner tube, I have another inner tube. And the principle is very simple. We advance just like we did before. The core sample now feeds into the inner tube. And then all I need to do is, when I've finished drilling my core barrel length, I retrieve it to surface, I now extract that inner tube. And typically what we do is the inner tubes are longitudinally split. So it's like in two halves. You can see from this picture on the left what I mean. So that when I extract it, all I need to do is take the top part off, and I've got this beautiful sample. And I can now do some work on that sample. So we use triple tube core barrels where the process of extracting the sample will destroy the sample. It allows us to get a much better core quality than we will with a double tube core barrel. So the principle here, guys, is very, very simple. We've got single tube, double tube, and triple tube core barrels. As you move from single tube to double tube to triple tube, the material, this is quite hard to understand, I guess, the wall thickness of the steel tubing that the core barrel is made of has to get thinner and thinner and thinner. And so as these core barrels get more sophisticated, the materials get thinner and thinner and thinner, the cost just rockets. It gets very, very, very expensive. To give you an idea, I'm a little bit out of things now. I'm not in the commercial side of the business anymore, but a set of split inner tubes like this for an NQ core barrel, I might be telling lies. Some of you guys might be able to correct me now, but those would cost probably in the order of about 5,000 Rand a pair. 5,000 Rand, put that into US dollars, it's about a Big Mac and a Coke. It's extremely expensive. And so as these core barrels get more sophisticated, the cost gets more and more, gets greater and greater. The other thing we've got to understand is that for a given hole size, if I'm drilling an N-size borehole, for example, if I drill single tube with a single tube core barrel, I'll get a big sample. If I drill double tube, my sample will be smaller. If I drill triple tube, it will be even smaller, because I've got to get more tubes into that dimension. And that's an important thing to understand as well here with these core barrels. Okay. So what I want you to take away from this, and I mean, we've rushed through this very, very quickly, unfortunately. What I want you to take away from this is the core barrel is critical. And the more you know about core barrel sizes, available sizes and designs, the better you will be at trying to understand the kinds of samples you can get and that you can't get from particular formations. Okay, so what we've spoken about there in this first part is we spoke about conventional core barrels. Core barrels where we've got to pull and lower every time we've advanced the borehole. Those are called conventional core barrels. Now, in a wireline core barrel, this is the second way that we can retrieve core from a borehole. In a wireline core barrel, I've shown this schematically here, and I'll show you pictures now of what a wireline core barrel looks like. In a wireline core barrel, we have a retrievable inner tube. So it's a double tube core barrel, but the inner tube can be retrieved. So it's a loose fitting thing. If you look here, I'll show you actual pictures in a minute. This is what the inner tube looks like. So the core barrel's down the bottom of the hole here, but this inner tube can be pulled to surface. We leave the drill string in the hole. The entire drill string remains in the hole. We lower a special device called an overshot. It latches onto the top of the inner tube, and we pull the inner tube to surface. We then disassemble the inner tube, extract the core, reassemble the inner tube, and we merely drop it back down the hole. It floats back into position in the core barrel. It locks in position, and I can carry on drilling. So a wireline retrieval system, as I've explained it here, is very much more efficient than a conventional system. To give you some idea, one of the very first deep boreholes I ever worked on in South Africa as a young man, many, many years ago, was a hole that was 3,800 meters deep. And the contractor was drilling, and at 3,800 odd meters, they entered an overpressured shale band. They had the shale band, and as soon as they drilled, the shale relieved into the hole. So we've got these long, very sharp slivers of shale that kept on essentially exploding into the borehole. And we couldn't advance the hole. So I was asked to go along, and we ran a special mud system, a special drilling fluid system to try and overcome the problem. On that hole at 3,800 meters, we were drilling with a 3-meter conventional core barrel. And it took us about 40 minutes to drill 3 meters. It took 13 hours to pull the drill string out the hole, and 12 hours to go back into the hole. So it took 25 hours a day to pull and lower. So in those days, for those guys who are not from South Africa, I was working at it. This project was about 130 kilometers from my home in Johannesburg. So I would get in my car, I would drive to site. I'd get to site just before they got back to bottom. We would start drilling. We would drill for 40 minutes. I'd then get in my car, drive back to Johannesburg, do a day's work, sleep, and then go back the next day. So the deeper the hole gets, conventional systems become more and more time intensive, and therefore really, really inefficient. So a wireline system was developed to make it more productive, more quick. So the principle is very simple. We have our core barrel down the bottom. We advance, we fill the core barrel, we fill the inner tube. I lower the special device, I pick up the inner tube, and I pull it to surface, as I've shown in the second picture here. Once I've disassembled the barrel, removed the core, I reassemble the inner tube, and I merely drop it back down the drill rods. The drill string is water filled, so it floats in the drilling fluid back down to bottom. It latches in the core barrel. I can then advance my next 3 meters or 6 meters, wherever long my core barrel is, and that's how I advance my hole. So now a wireline core barrel is a little bit more complex, a little bit more complicated. I'm just going to show you the basic outline here of what a wireline a core barrel looks like. Just like our other core barrels, it has different components. It has the reaming shell and the drill bit at the bottom. It has an outer tube, and then it's got a few special things at the top. Don't worry about those. We call them adapter coupling and a locking coupling. But that's the outer tube. That's the part that will remain down the hole. And then we have what we call the inner tube. And the inner tube is the part that's retrievable. And if you look at the top of my picture, you see this little pointy thing at the top. We call that the spearhead. And that's the part that the overshot latches onto when it pulls it out. It's much more complicated than we've got time to talk about today. But essentially, this is the retrievable part. And this lower part here, this part here that I painted gray on my little sample here, this is what we call the inner tube. And that is the part that accepts the core. So as we advance, the core sample feeds into that inner tube. And that inner tube will either be 3 meters long. We can adapt them to make them 6 meters long. So therefore, I can advance my hole either 3 meters or 6 meters. I then need to stop, retrieve that inner tube, disassemble, remove the core, reassemble, and drop it back down the hole. And that's the basic principle of a wireline core barrel assembly. Much more complicated than I've spoken about. We can spend days talking about this, but we just don't have that time today. Okay, so there we've chatted now about the first part of what I wanted to speak about the technical aspects of a drilling operation. What we spoke about there in just what is that, about an hour and 20 minutes. We have online training programs where it takes us 6 months to talk about this stuff in detail. It's much more complex than I've spoken about, but all I want you to do is to have an appreciation of how we drill, what those critical elements are, and some of the factors that can affect the representativity and quality of your samples. Whenever I'm asked to talk to geos, one of the key pieces of advice I give them is I say to them, please be inquisitive. When you go to a drill site, whether you're visiting or it's a drill site that you're running, ask questions, ask questions, ask questions. When I started this industry, that's how I got to know what I know. I just asked hundreds of questions. And don't always believe the first answer you get, because very often it's not right. Ask the question more than once. And learn as much as you possibly can about those technical, those physical aspects of a drilling operation. The more you understand, the more you'll be able to influence the operation to get the kind of sample quality you want. And that's the key part of that first part. Let's talk now about the second part. Now, I'm going to just talk more philosophically than anything kind of any sort of nitty-gritty. Geos need to know about safety aspects of drilling. And so you need to know about the risks and the hazards that exist on drill sites. And as I said earlier, one of the key things you need to know as well is what your legal liability is, what your legal responsibilities are. And in different jurisdictions in the world, there's different legislation that govern safety on drill sites. In some countries, in Canada, for example, in Australia, there is legislation that is specific to drilling. In many jurisdictions of the world, in many countries, the law is silent. It doesn't say anything about drilling. In South Africa, we've got a very big drilling industry in this country and a very big mining industry, but none of our legislation talks to drilling. And that's where one of the big challenges is, because what you've got to do is you've got to look at the law, you've got to look at that legislation, and you've got to interpret it and extract from it what applies to a drilling operation. And that can be very, very difficult. So you need to have some knowledge of the law and so on. It becomes very difficult. But I urge you, irrespective of where you're working in the world, try to find out what your legal liability is and what your legal responsibilities are, because in some parts of the world, you don't want to go to jail. In no parts of the world you want to go to jail, but some parts particularly you don't want to go to jail, because it won't be terribly pleasant. So the best way I can explain this to you guys is like this. I'm very lucky. Over the years, I've become deeply involved in aspects of safety with drill rigs, and I've been involved in writing safety standards for mining companies, and involved in safety audits and all sorts of things like that. And I want to explain it like this. This little logo here, this little picture you see is a logo that's part of my corporate, if I can call it that, a sort of brand identity. I think that's the term people use. But in all of my literature and all of my training programs, you will see this little logo. And it encompasses what we need to know, or at least gives us a guideline to what we need to know about safety on a drill site. I believe that drill site safety revolves around 4 aspects. Number 1, the equipment, the drill rig, the compressor, the trailer, the lighting plant, the pump unit, the driller's shack, all of the equipment that we use on the drill site. And all of that equipment has inherent risk attached to it. So we need to understand all of the risk associated with that equipment. Now, mining companies tend to be fixated on equipment, and mining companies think, and I'm not being disrespectful at all, mining companies, I do lots and lots of work for mining companies. If there weren't mining companies, I wouldn't have any work. But many mining companies tend to be fixated on equipment, and they think that if we automate everything, we've managed risk. That's not true, because we unfortunately have got to have people. If we've got a totally automated drilling operation, this argument might fall away. But right now, we've got to have people on a drill rig. And we've got to have people, number one, to operate the rig. We've got to have people to maintain the rig. And more importantly, we've got people to repair the rig. So if that equipment, as automated as it may be, as soon as we put a person anywhere near a piece of powered equipment, we're at risk. And we need to understand the risk. And very often we don't. I believe the biggest exposure we have in a drilling operation is people. There's no limit to what a person can do. A person can take the most simple situation and turn it into a catastrophic disaster just by making a bad decision or making a bad action or forgetting to do something. So we mustn't forget that unless the process is totally automated, we've got to have people involved. And so that leads us then to the third aspect of safety on a drill site, and that's the processes or the procedures. The one way that we can make sure that equipment and people interact correctly is to have the correct procedures. And so that means we need to understand how the equipment works. We need to understand how we pull rods. We need to understand how we pull the inner tube. We need to understand how we change a bit. We need to understand how we carry out maintenance on a drill rig or repairs, how to change a hydraulic cylinder, how to clear a blocked sample hose, all of these things. These are all covered by processes. And we need to understand how people use the processes to operate the equipment. You can see this sort of triangle, if you like. And if we understand all of that, we could then start to manage safety on drill sites. And very often what I see in many operations is the people aspect is not properly understood, and the process aspect is not properly understood. And those three things are very, very important. Then the fourth aspect we've got to consider is the local working environment. And what I mean by this is that a process that is perfectly adequate when we're drilling on a farmland in the middle of a maize field, for example, that process might not be adequate if we're drilling on the side of a hill at high altitude. And so what we've got to do is we've got to consider how we modify the processes that we use for any particular local environmental condition. High heat, dust, wind, rain, etc., 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 because it will alter the processes. And my belief is that if we understand those four aspects, we truly understand them, we can then start managing drill site safety. It's a lot more complex than that. But I think if you guys can remember this picture, if you want to copy the picture, you just tell Tanya, stick us a message on the chat line and we'll send it to you. But I truly believe that drill site safety revolves around these four aspects. And if we understand these and we manage them, I think we can manage safety on a drill site. The last bit I want to talk about today, the last aspects that I think a geo needs to understand or know something about are economic aspects of drilling. I'm going to talk a little bit longer and maybe with a little bit more passion because, again, it's part of the industry that I'm very lucky. I've become more and more involved in managing, or not managing, that's the wrong word, in assisting in developing the development of tenders and the evaluation of tenders. And I've seen how dramatic an impact a poorly designed contract can have on a drilling operation. So I just want to talk a little bit more about that, and then we'll call it a day, and we'll have some questions. Okay, so let's talk about some economic aspects of drilling. Some of you may have already been involved in drilling contracts. Some of you may not, but at some point in time as a geo, you are going to be. And all exploration drilling, there might be a small amount that is, but all exploration drilling is based on a contract. The mining company or the exploration company has some work to do. They'll develop a tender specification. They'll go out to tender. A whole bunch of contractors will bid. The contractors, the bids will be evaluated, and they'll say, we want this guy to drill for us. And there will then be a contract that will specify, hopefully will specify the work to be done, all the ifs and ands and buts, and what the prices will be paid for the particular work that is done. So all drilling, 99% of exploration drilling is based on a contract. And so it's very important for the geologist to understanding of how that contract is structured, because that contract, the structure of the contract will very much dictate the relationship there is between the geologist and the contractor. It'll dictate what impact the geologist has on the contract, and the impact that the geologist has on whether the contractor makes profit or not, whether he makes money or not, whether he survives or not, whether he's around to bid on the next contract. And so we'll talk about a few of these aspects now. Okay, give me 1 second. I just want to try and get my pointer to work again. Okay, let's look at a couple of basics here. In a typical, what we call a variable rate contract, okay, the typical drilling contract, you'll have the mining company or the exploration company that has a fixed budget. You've got a certain amount of money that you have got to spend, and you want to get as much information as possible. So you've designed your budget, you've designed your project that you want to drill 20,000 meters or 15,000 meters or 150,000 meters. So what you would like, what the mining company wants, is the lowest cost per meter, because the lower the cost per meter, the more information you're going to get. Unfortunately, you've got the contractor, and the contractor has massive investment, huge amounts of capital invested in equipment, in drill rods and downhole tools, in ancillary equipment, lighting plants, compressors, etc., etc. Massive capital investment, huge. A modern day drill rig now, diamond drill, will cost you anything from 6 to 14 million South African rands, whatever that is in real money, but significant amounts of money. And the contractor has to maximize profit, because he's got to maintain that equipment, he's got to replace that equipment, he's got to meet certain safety standards. He has to make a profit. He wants to maximize his profit. And so he wants the highest price per meter or the highest rate per meter. There's a very big difference between the cost per meter and the rate. In other words, between what he says he's going to bill you and what you actually get billed. There's a very big difference. But he needs to make as much money as he possibly can. So between these two seeming extremes, you've got to come up with a contract. You've got to come up with a contract that allows the mining company to get its information and the contractor to survive, for him to be able to bid on the next contract. And I use that word very advisedly. Many mining companies, this sounds very contentious, but maybe it sounds rude. Many mining companies, you would think that their objective is to put the contractor out of business. That's not what a drilling contract's about. You want the contractor there in a better position to do better work for you next time. So the contractor's got to be correctly structured. And unfortunately, what happens when we drill, we drill because we don't know what's down there, and things change. But very often, the scope of the contract changes. The contract says we're going to drill vertical holes, and you drill 4 vertical holes. The geo says, oh dear, we want to drill angle holes now. That changes the nature of the project completely. It changes how quickly the contractor can drill. It changes the rate at which his equipment wears, etc., etc. And you can't do that. You can't just change the scope of a contract because you haven't planned correctly. So scope creep is a very big very big factor. So we've got to make sure that doesn't happen, or we stop it from happening. And I wanted two things here, guys. This next slide is probably one of the most important slides in this little talk today. And please, I want you to remember these two principles here. There's two basic principles of business that we must not forget. When I say business, contracting, mining, you name it, these same principles apply to every aspect of business. The first principle is this: if a contractor is not making a profit, he will not perform on site. A contractor has to make a profit. He's got to pay salaries, he's got to train people, he's got to repair equipment, he's got to replace equipment, he's got to buy new vehicles. He cannot do that if he's not making a profit. He has to make a profit. And I argue very often with customers of companies I work with, it is more important for a mining company or an exploration company to know that a contractor is losing money than is to know how much money he's making. Very often we think, oh, the ex making too much money, the guy's making too much money. It's more important to know that if he's losing money, because I promise you, if he's losing money, he's going to have an accident. And then your life's going to become a misery. Then your whole project becomes a problem. So the contractor has to make a profit. And so in selecting the contractor, select the contractor correctly. Don't always go for the cheapest contractor, because you don't always get the best from the cheapest contractor. So that whole, we can spend 4 days talking about that, but please remember this: the contractor has to make a profit. The second principle is that profit is the reward for risk. So when you design your tender specification, a tender specification must understand and it must address risk in drilling. We drill boreholes because we don't know what's down there. There's all sorts of geological issues, there's mechanical issues, all sorts of things that can go wrong in drilling a borehole. If the contract places that risk on the driller, on the contractor, expect to pay a high price. However, if you can identify the risk, if you can properly assess that risk and apportion the risk, let the contractor carry the risk that he can manage, and let the mining company carry the risk that they can manage, you get a far more equitable contract. But very often what you see is all the risk is placed on the contractor. And if that's the case, then you must expect very, very high prices. What tends to happen nowadays, in the exploration business now, in many parts of the world, there's fewer contractors than there is work. And so what you tend to see is contractors now try to structure or influence contracts so that the mining company carries all the risk and they carry very little risk. This is just one of the dynamics of business. But it's just very important to understand that if we ask the contractor to carry all the geological and the mechanical and the economic risk and the community unrest risks, then we must expect to pay a very, very significant price for that for that benefit. I want to show you just quickly last couple of slides, and then we're going to call it a day. Okay. In a drilling contract, every drilling contract will ask the contractor to submit a schedule of rates. He's going to charge you this and this and this and this for different aspects of work. And I want to talk very quickly about how, and this is very simplistic, guys, but very simplistically, how a contractor calculates his prices, how he would work out what he's going to charge you to drill. A contractor will have two basic elements of cost. There are fixed costs. These are costs that he pays every month, whether he is going to, sorry guys, he's going to pay whether he's drilling or not. These are fixed costs. So he's going to have salaries and wages. He's going to have rentals. He's going to have amortization payments on his equipment. He's going to have insurance, etc., etc., etc. Whether he's drilling or not, he's going to have these fixed costs. And those are, generally speaking, big chunks of cost. Then he will have also variable costs. And these are costs that he will incur only when he's drilling: fuel, bits, drilling fluids, oils and greases, etc., etc., etc. So he's going to have fixed costs and he's going to have variable costs. And so what the contractor will do, when he's got to work out how much he's going to charge you, how much he's going to put in his tender document, how much he's going to put in his bid to drill a meter, he's going to look at his fixed costs, and he's going to look at that scope of work that you've developed. And he's going to say, okay, based on the conditions they've told me there will be on this mine, on this particular project, I reckon I can drill 1,000 meters a month, or I can drill 500 meters a month, or I can drill 900 meters a month. And you'll take those fixed costs and you'll divide by either 1,000 or 900 or 500, and you will get a fixed cost per meter. So the information you give him in that scope of work is critical, because if he gets that estimated number of meters wrong, he's either going to be above the line or below the line. He's going to make money or he's going to lose money. So it becomes very important that that scope of work is clear. Then what he will do is he will add, please move on quickly, he will add to that fixed cost per meter his variable cost per meter. Now, the variable cost meter, he will base this on historic information and results he's had previously. He reckons it costs $25 a meter to drill NQ boreholes, or it costs $35 a meter, whatever the case happens to be. But that'll be another estimate that he has to make. So as an example here, and I'll go through this slowly, very important for us to understand this. Let's assume that a contractor's fixed total costs are $150,000 per month, and his variable costs are $35 per meter. So that's his bits, fuel, blah, blah, blah. Those are the variable costs that he's going to incur. And based on what we've told him in that tender document, he reckons he can drill 900 meters a month. He says that's how much he's going to drill. So he will take his fixed costs, $150,000, he'll divide by 900, and he gets $167 per meter. That's his fixed cost per meter. Then to that, he will add his variable cost, 35, and he'll say, okay, this project is going to cost me $202 per meter to drill. And then he'll add a profit margin. We'll talk about that just now. He'll add a profit margin to that, and he'll put that price into the mining company. And that will be the price that you're going to use to evaluate this. Now, the key thing I want to get through here, guys, is this. In putting that tender document together, you rushed it over the weekend because you wanted to go and watch a soccer game, and you didn't give the guy all the information. And because you didn't give him all the information, he's not going to drill 900 meters a month. He's going to drill 700 meters a month. So his fixed costs now are not going to be 150,000 divided by 900. It's going to be 150,000 divided by 700. So all of a sudden, his costs have rocketed. And that's the basic principle that I want to get across in this little part of this section. We have to be equitable in a drilling contract. In a drilling contract, the mining company have to get their information. And the only way you're going to get that information is by having a contractor. And so treat him fairly. Specify the work correctly. You can then evaluate your bids correctly. So that's a very important principle I want to explain there. Last couple of slides, and then we're going to call it a day. Okay, the timing has worked out absolutely perfectly. There are different types of drilling contract. Back in the good old days when there was not much work around and contractors had to compete very closely with one another to get work, some contractors quoted what they called in an all-in rate. So they told you it's going to cost you this much per borehole. It's a one-line invoice. I drilled 2.5 boreholes this month at this much per borehole, and that's how much you owe me. Very risky for the contractor, but in certain conditions you can do that. The more common type of drilling contracts, what we call a variable rate contract, like I've just explained now, where the contractor will bid certain rates for different elements of work, different types of work. And then the last one was also popular a while ago, and starting to come back a little bit more now into expression, is what we call a fixed rate contract, where the contractor says, I will bring my drill rig to your mine, and you're going to pay me $200,000 a month for the pleasure of having that drill on your mine. And then if we do drill, I'm going to charge you so much per meter. And this type of contract works very well, very well where you have intermittent work in remote locations where it's hard to mobilize a drill rig and demobilize a drill rig. And in many cases, many contracts, many projects have been done very, very well on a fixed rate basis. So you need to have a little bit of an understanding of what kind of contract you have, because that will allow you to determine where you can influence or what you do to influence whether the contractor makes or loses money. Because that is important. The geologist can have a huge influence on the profitability of the contractor and therefore the efficiency of the contract. And I always end this off by saying, be kind to the contractor. If it's a bad contractor, you made a bad mistake, you might have to live with that. But if it's a good contractor, help him. Don't give him money. Well, I'm not saying that, but do not stop the contractor making money through unreasonable actions. And that's kind of what I'm trying to say there. Okay, so the timing is absolutely perfect, down to the minute. So to summarize quickly, I believe from a drilling perspective, you need to understand technical aspects, safety aspects, and some economic aspects of your operation. And as I said earlier, I suppose the best advice that I can give you based on my years of working in the industry and working with many geos, be inquisitive. Geos by nature are inquisitive people. Otherwise, he wouldn't have been a geologist, I guess. But be inquisitive. Ask questions. Don't believe the first answer you get and sift the wheat from the chaff. But learn as much as you can about these aspects. Because unfortunately, modern day exploration requirements require that a geologist is not just good at looking at rocks. A geologist has to be good at all of these aspects here. And the more experience you get, the more detailed knowledge you get, I think the better you will be at what you're asked to do there. Okay, Tanya, I'm done. Perfect timing. Absolutely perfect. I expect to finish at 20 past, so we've got some time for questions if we do, and then you guys can break for tea. Guys, I don't know if there are any questions. Tanya, do you want to see, have we got any questions?
We do have a couple of questions in the chat box. I want to start off with Andrea's question. Okay. What is the impact of no flushing system? Is generating an inner tube that can be removed with no impact on the sample, and the inner tube splits open upon removal a reasonable way if you cannot use a flush system?
Hey, Andrew, that's a very interesting question. I think I understand what you're saying. In some rock types, particularly, for example, if we're drilling into rock types that are water sensitive, kimberlites, formations that are high in clay mineral, mudstones, some shales, for example, the drilling fluid, the water-based drilling fluid, the water fraction, can react with the rock, with the clay chemicals in the rock, or it might be a potash, for example. It might chemically react with a formation and cause hole enlargement. And very often we want to try and drill without a flushing system. It's very hard. It's very hard because in any drilling operation we create cutting. It's the purpose of it. We fragment rock, and when we fragment that rock, we have to get that cutting out the hole. And if you haven't got a flushing system, you can't get that out the hole. So we can, Andrew, I think I know what you're talking about. We can drill without a flushing system for a very short distance, and we can still pull the drill string out and go back to bottom. But we can't do that forever, because we've got to get the cutting out the hole. So, Andrew, I don't know if that answers your question. I don't know if I've misunderstood what you were asking there. If not, then just pop another question on there, okay? All right.
Okay, next question from Answer Beloy. Why is the focus on the hole size and not core size? What impact does a bigger hole have? Why would one go for a diamond bit with higher diameter if the same results can be obtained with a relatively smaller diameter? I ask this because different designs often imply different bit sizes, which leads to different hole sizes.
Answer absolutely spot on, sir. Very good. This is more an observation, I guess, than a question, but you're absolutely correct. The focus, generally speaking, in designing a borehole, the geo will know the minimum core size, the minimum sample volume that you require to do your various tests. And so you're absolutely correct. The core size is correct, 100%. If, however, we want to, after the hole is complete, we will run some geophysical probes, do some geophysical work in a borehole. That requires a certain hole size. I'm involved in some projects now where at depth we want to run some geophysical probes, and there's a big debate. Do we drill an NQ hole that's 76 millimeter or an HQ hole at 96? HQ hole is much more comfortable for our probes, but it's a hell of a lot more expensive. So to some extent, hole size can play a role as well if we're going to run some geophysical probes. But you are totally correct. There's no point just drilling a big hole because we want and get a small core sample. It's a balance, and that's why an understanding of different core barrels and the hole size and the core size is important for a geo to understand. And I hope that answers your question, but it's a very good observation. You obviously involved in some work because you worded your question very, very smartly. I hope I've answered it. Should we move on? Let's see.
Andrea has a follow-up question to her previous question.
Yes.
What is the depth that we can look at? Would it be less than 1 meter?
Oh, Andrea, ask me who's going to win the next World Cup. Yeah, look, it depends upon how you're drilling and the bit size and so on. But yes, I guess that order of magnitude, yes. I would say that order of magnitude is around about 1 meter, drilling with no flushing system. I would guess that order of magnitude. If you want to, you're more than welcome to give me a buzz sometime and we can chat specifically through what you're talking about doing there. Maybe I can give you a better answer. But yes, that order of magnitude, I would say you're about right.
Okay, we have another question from Chipejo. How
Yes.
do you solve water contamination of samples in, Chipejo, you're in trouble, in RC drilling if the compressor is not strong enough to create the needed flushing velocity of chips?
Okay, Chipejo, great answer. I should refuse to answer this question on the basis that you use the term RC and not dual tube RC, but we'll let you off this time. Okay, it's a good question, Chipejo. Guys, in an RC drilling system, a dual tube RC system, as we spoke about earlier, it's a pneumatic system, and if we drill below the water table, we'll have water ingress into the hole. Now, one of the theories behind RC drilling is the pressure of the air as it flows past the bit will be sufficient to keep the water out. So you won't have water flowing into the borehole. So you theoretically, drilling RC below the water table, you should be able to get a dry sample coming out the top, or at worst, a dampish sample. But the deeper you drill below the water table, the greater the hydrostatic pressure of the water, and the more likely it is to flow into the borehole. And it then becomes a function of the size of your compressor. That's wrong. The pressure output of your compressor. If you've got a very high pressure compressor or a booster, you can keep the water out. If you haven't, you can't. So, Chipejo, the short answer, sir, is that if the output pressure of your compressor is not sufficient to keep the water out, you're going to get a wet sample. There's not much more you can do. And that's why they use boosters on deep dual tube RC holes. So there's not a great deal you can do there, unfortunately. Should we look at Geological there?
Yes.
My question is with regards to percussion drilling. How do we validate the depth of the hole against the given depth by the driller operator on site? I understand there's cases where you have the core barrel sticking out on surface. Let me read this again. My question with regards to percussion drilling. How do we validate the depth of the hole against the given depth by the drilling operator? I'm not sure about the last part here. I understand there's cases where you have the core barrel sticking out on surface. I understand that, but let's just look at the first part of the question here. How do you validate the depth of the hole against the given depth by the drilling operator? Okay, I think I understand here what you're saying, Geological. I said earlier, guys, that hole depth is obviously critical. It's no good drilling if we don't know where the heck we are. And I can tell you, with no disrespect to anyone, I can tell you that very, very frequently hole depths are incorrectly reported. So we have to know how to measure hole depth. And I'm going to try and do this with my fingers. I'm going to see if you understand. When we measure hole depth, we measure hole depth using what we call a stick up. So let's look at it this way. I've got a certain number of drill rods. I know they're all 3 meters and I can multiply by 3. Then I've got my core barrel or downhole hammer or whatever else I've got at the bottom of the drill string. So that is my total drill string length. So when I drill, for me to calculate the depth of the borehole, all I've got to calculate or measure is how much of the drill string is sticking up above ground level. And then I can measure this. It's just not so easy to do, but you've got to work out a way to do that. You've got to measure the length of the drill string sticking above ground level. So therefore, I can calculate what's below ground level, and I've got my hole depth. We've got to do that all the time. You've got to check depth all the time, particularly in deep holes. In one of the training programs we do, one of our online training programs, it's a question I ask geos, and I've had hundreds, literally hundreds of geologists go through our Drilling Skills for Geologists program. And I think I've had 4 people who've ever been able to explain to me correctly how to check borehole depth. So it's done by what we call a stick-up method.
I would like to thank all for this opportunity to quickly take you all through some of the products we have developed for the industry. Firstly, and at its core, UCP Africa provides its clients with a holistic core storage solution, which offers a multitude of design benefits for our users, from quick and easy on-site assembly to improved handling ability and even improved access and visibility of your core while it lies inside the core drive. Our products have been specifically designed with the geologist and the geological workflows in mind. Now I'd like to discuss some of the projects that we have been working on over the last few months. And firstly, let's start with the all-new Scanned Photos application. Finally, you can put your core set into your pocket for free with the all-new Scanned Photos app by UCP Africa. It is a simple iPhone app which can import, capture, rename, sort, and export multiple projects' core drive photographs, all in one convenient location. You simply swipe to browse through your boreholes and inspect any core drive photos of interest at the push of a button. Digitizing and sharing your borehole core drive photographs has never been easier, and even more, never rename your core drive photographs again. Okay. Once you have digitized your borehole, you can now log the core digitally using Scan It. It is purpose-built workstation software program where geologists are able to geologically, structurally, and geotechnically log their boreholes. It is time efficient, accurate, and precise, and ScanIt can improve your workflows and data collection abilities. It is a software program developed as a tool to allow geoscientists to obtain and control data and information quickly and easily. Once you've logged, you can access your data in 3 of the ScanIt display modules. The first being the 3-dimensional orthographic representation, where users can visualize the recorded information in real space orientation. You can even observe how some features may possibly interact with other recorded features in your borehole. You can also expand any of the planes of that you're interested in, and even export this as a DXF file to be used in any CAD-based modeling program. Then we have the ScanIt StereoNet, where users can view poles to plane, grade circles, and even display calculated means of poles to observe any potential lines of intersection which might be occurring. Means are displayed using showing the calculated standard deviations as well. And at the click of the mouse, ScanIt will display the plunge and trend of any line of intersection displayed. And lastly, in our composite log, where users can view a stitched image of the core alongside the recorded information. Finally, users can scroll from surface to target and access generated information alongside an actual image of the core. This projection can also be exported via PDF or PNG, and it can be shared amongst your team, and it can even be attached to specific reports. It's just one of the many ways we at UCP Africa can add value to you and your projects. Information generated by ScanIt can be exported into an Excel spreadsheet where you can access and validate your data with ease. It is fully customizable and integratable with your database management software. ScanIt can save you time and improve your data collection. Please feel free to visit our website for more information on ScanIt and many of our other products we have developed for the industry. And I would like to thank you very much for this opportunity. Should anyone have any questions, please do not hesitate to contact us for assistance. Once again, thank you for your time.
Thank you very much, Colleen, and thank you very much to UCP Africa for your annual sponsorship. We do appreciate it.
As Tanya said, I'll be talking to you about what geologists need to know about borehole logging. And for the purposes of bandwidth, I'll then switch off my camera. So the presentation is structured into six sub topics. And I think building on a lot of what Colin has already touched on the drilling. And I think it's very important that we not forget that part, because a lot of it and good drilling informs good geology afterwards. The key thing for me, though, is all of this needs to be done and executed with the end in mind. So we'll go through the context setting and how to wrap our heads around what the end goal of logging is about. Talk briefly and touch base again on the drill management and those aspects that Colin was referring to in terms of what geos need to be looking out for in the drill sites and managing a drill site. And obviously that goes with quality assurance and quality control principles. Logging, then we'll get into the details of what goes into a database, because logging is a data collection process, and then the end in mind, connecting the dots. Before we jump right into it, disclaimer, as you've seen, I'm an employee of the Kumba, a division of Anglo American, and I am a fellow of the Geological Society and registered with SACNASP. Even though my time is sponsored by the business, I am, although dedicating my time to this event on my personal capacity and not as a representative of Anglo-American or the GSSA or SACNASP for that matter. As such, any opinions I share here are attributable only to self. So in terms of setting the context, we're dealing with, when you're drilling exploration, you're dealing with a mineralization targeting an ore body. And these are 3D entities that occur on surfaces of the earth. And the critical aspect here is to remember that we're dealing with a mineral system. We map and we present the data in 2 dimensions, typically an XYZ. The coordinate systems vary across the world and across businesses. Where drilling comes in place is completing the picture on the 3rd dimension. And typically, if we can't drill, we look at road cuts or river cuts or trenches. But the more relied and called upon method of completing the 3rd dimension, the Z-axis, is drilling. The criticality to also remember is that if you're working in a major company, this information leads up to listing information that goes into the stock exchanges, supported by R&R statements. And the part we're going to dwell a lot on is on the mineral resource side of the conversation, where with increasing confidence, you're decreasing the risk in the deposit. And typically the big players are looking at deposits that are spanning in the 30 to 50 year span of operation. And where drilling then fits in that value chain, you'd start maybe roughly the first 10 years of a target in your exploration phase, where prospecting and resource estimation are critical components of your drilling strategy. Goes into the planning phase, and this is where your mining engineering and metallurgy specialists come in play in terms of assisting, completing the modifying factors that convert your resource into a reserve. And construction comes only after we've decided that the deposit is carrying a reasonable prospect of eventual economic extraction, and leading up and setting up your mining and your development post exploration and extraction of the mineral. The key thing I think for me in this conversation is that most geos forget about the principles of drilling and the principles of this framework past the construction phase. When it comes to actual exploration, there's 2 critical opportunities that involve a geologist. It's the geometallurgy space, where the nature of the ore body evolves over time, and the ore body itself, the extraction properties are not a linear extraction that you can base on your initial set of exploration results. You have to set yourself up as a learning organization and as a learning geo, being curious, as Colin said, to test and still satisfy yourself that your ore body is, you at least understand how it behaves in the beneficiation process. There is, of course, also opportunities of what we call brownfield exploration. That's typically the conversations around if it's within the tenement or the mining right, where life of mine expansion happens. These are things that are typically outside your budget cycles, beyond 5 years of your current life. Some operations operate for 100 years with a 5-year life of mine, which tells you that they are very conservative in terms of work in that brownfield space, but nonetheless, the positive here it is being done. So getting into then the discussion around mineral systems and the basics of tire generation, there are 4 critical components that lead up to an economic deposit. And the key thing here, economic deposits are anomalies in the surface of the earth, and the factors that lead to the concentration are very dependent on what deposit you deal with. But the critical factors is that you need a ligand, typically, and this is a conversation around metal deposits, a ligand being the one aspect that attaches or binds to the metal you're after. You need a source to extract the metal from. It could be an existing rock, it could be a volcanic emplacement, whatever the type of deposit you're dealing with. You need plumbing and a pathway for those fluids and the ligands to migrate to a particular setting. And the third component is the trap, where the deposit occurs, where you trap and concentrate the deposit, and obviously then flush out the system, being the fourth. And the outflow, what you want is the remainder of the fluid, not to dilute your economies of scale in the deposit, to flush out the remainder of the fluid. And this framework really is, in my view, applicable to almost all the deposits you can think of. You just need to understand the style of emplacement and the mode of mineral occurrence that would lead to how you define these four components. Applying and understanding this framework is, for me, one of the basic components around understanding what your role in a drilling campaign as a geologist starts off with. The important relationship to that is the major geologic and tectonic events, where here just illustrating is that closely related to the major tectonic events in the Earth's history, there's been significant deposits that have been emplaced, and understanding that relationship of major tectonics is important as well as an input into how you set up your understanding of the context within which the drilling is happening. For example, if you look at in the South African case, with the Bushveld complex being the biggest PGE deposit you can think of, the major tectonic events around 2 billion years, and you see the spike there. In the iron ore space, you see a lot of superior type deposits pitching up just before the 2 billion mark, between 2.5 and then 2 billion mark. That does not mean those time horizons are the only time horizons you need to be looking into to find economic deposits, but it certainly highlights the fact that understanding your tectonic history is fundamental to understanding the context within which you're dealing with the drilling, which you have to log afterwards. And that goes with the field regional settings. This is an image of the terrain within which Kumba operates, looking for iron ore. And obviously, as I've mentioned, maps are two-dimensional features, but the equally important is what do you see in the field? And this being an image I took on a particular site, looking roughly northwards, you would basically as a geo familiarize yourself with what the layout of the land looks like, because remember, a drill hole is a spot on the surface of the earth, and everything that you interpret or you log in the process and describe needs to be consistent with the two dimensions that you see on the surface of the earth. It cannot be that the field settings tell you one thing and a borehole tells you another. The disparity between those two things, that's where your geology skills are called to action to explain that difference. If the difference is scientific, that's what you need to be guiding the conversation towards. If the difference is related to what Colin was referring to in terms of mishandling the samples, then you need to be awake to those potential pitfalls and manage them proactively. So going into one of these things to see is on the left-hand side is the stratigraphic succession of the area I just showed you. On the right-hand side is what you typically see on the borehole. And understanding this, you'd realize that it does happen that the stratigraphic succession is put in sequence, in time sequence and chronology, but in your encounter, things might be jumbled up. And being able to see, for example, here, the case group, which sits at the top, is sandwiched between two older parts of the Transvaal supergroup. And there are telltales and markers in your core that tells you of this relationship. And this is why it becomes important as a geo to not only think of a drill exercise or drilling campaign as putting a number of holes in the ground. It's instead, as Colin captured it, is an exercise of retrieving representative samples of the targets you're after. And those telltale signs can easily be lost if your drill samples are being mismanaged. So drills, Colin has probably showed a few pictures of this. This is a Roco drill. One of the sponsors of the event, Rosont, owns and manufactures these drill rigs. They are the older fleet they would have spoken about. Still very reliable and good machine to work with for diamond drilling specifically. And the key thing for me here talks to the fact that be cognizant of the environment as well, the environmental factors, because you'd see in this environment, it's in a dry, harsh, desert, semi-arid area. So being able to conserve the environment as best as possible while it's still in the early stages of exploration is part of what a geo needs to be managing on site. That comes with specific site layouts and setups to minimize the footprint, to preserve portions of the topsoils and throw away the, Colin said, don't call it sludge, the cuttings. The cuttings he was referring to, you basically would put them and you dispose of those, you preserve the topsoil, and once you're done with the drilling, need to help the site rehabilitate while you're in the process of deciding whether that is economic to extract or not. I've been to a couple of historic drill sites where you find that the only thing the geos that pitched up in that site cared about was drilling the hole and left it. Some of the boreholes are still leaking diesel, being brought to the surface by the groundwater running up the hole, which is really untidy and not good for the environment. And it attaches to the legal considerations that Colin was referring to. In some instances, you might be dealing with drilling within a community. This was a drill site in the Eastern Bushveld site in a town called Beggersfort. It does happen that your mineralization extends within areas where people live, and being mindful of bylaws, municipal and traditional laws or customary laws that are applicable to the area you're working with is quite important. In this particular site, 24-hour drilling was a no-no, because you don't want to be having a drill rig noise at night close to people's houses. And even drilling within the day, you need to be considerate and sensitive that you are within a community, and make sure that you do not leave the area displeasing to the residents. This rig is one of the important developments in a technology sense. From my perspective as a geologist, is that when these conversations around technology start, people quickly think that it's a reduction of manpower, which is actually not the case. In this example, this machine actually has 2 operators instead of 1. Like this one, there's 1 drill operator. Here, there's 2. This machine is an automated rod handler system. Then in the front sits an operator that handles the rod handling system. And on the side here, facing the back of the picture, is the drill operator. And this is the rotation elements and the drive of the drilling action. There's even still newer versions where the 2 operators are still 2. But on our site, we have female operators, and they are in an enclosed cabin, which is still off the machine. The advantage of this machine is it considerably improves the safety management aspects, because most injuries you'll find on a drill sites are normally hand injuries because of size. And these are the things that as a geo need to carry in your understanding that it is not just about the hole in the ground. There are human beings that are going to be handling the samples that ultimately, as a geologist, you will be piecing together to tell a story of the Earth. Now, coming into the discussion around drill management, the first thing that needs to be crystal and clear is whether the drill campaign you're on is a brownfield or a greenfield exploration exercise. In the brownfield, the critical thing is here is that the mineralization style is mostly understood. And please never take a brownfield exercise as the geology or the genetic model is a done and concluded case. Geology is a very interesting exercise. Geology is a very interesting exercise, and I think the genetic model is typically regionally based. So it's important that you as a geo, you bring the understanding to a deposit scale. As you see here, showing from the geophysics, the bottom is an area that we know and there's mining existing. And slightly to the north of that, there's prospective mineralization occurrence, which occurs in a different modality than what is known currently. The management of your drill campaign is not about the hole in the ground, and I've said this already, and Colin has highlighted this. It is about the representativity of those samples, and it can make or break your project, particularly expansion projects. If you conduct an expansion exercise incorrectly, you could limit potential mining expansion discussions where the initial conversation was based on the first extraction, but there is potential of economic extraction. And the more cost effective your mining exercise is, the better you are able to expand the life of mine. But the cost-effective strategy relies on good and well-defined geology understanding. And Colin has already touched this, and I enjoy always talking after Colin because it's always about the curiosity, regardless whether it's your first year in the site or you are now the one managing the entire drill campaign across a province. The critical thing is always teach your eye to always look out for the thing that you haven't seen in the previous borehole, because that small and fundamental difference could be a telltale sign for something that you need to pay attention to. And much more importantly, you pay attention also to the human beings that you work with on that site. The rest of the conversation really, and you'd have seen by now, it's tailored for core drilling. We're going to be talking about diamond core drilling. As Colin has highlighted, this is an extraction of a cylindrical soil. Yeah, thanks, Ty. So core drilling extracts typically a cylindrical representation of the vertical or Z dimension of your area. And I say it's non-destructive to the internal structures of the rock, but obviously it is a destructive way of sampling because you disturbing the earth within you setting up the drill sites. But the key thing about core drilling, it is more representative of samples that of the in situ rock, and it requires a regular check and inspection of the drill quality, but the accuracy that you'll get out of the core exercise is much better than a ground or chips from a different type of drilling. The one thing though then to note, relatively speaking, core drilling is time consuming and it is cost expensive, and understanding the cost structures that Colin was talking about is fundamentally important, because you do not want to keep a driller drilling and struggling with a hole, especially if it's a technical issue in the drilling process, and incur unreasonable costs on the drilling side, because from that point on, the quality of sample that you will get is going to be a poor sample. Core sizes, Colin talked about this quite a lot. With the imperial system, which is used in North America, we typically work in the metric system, and the typical size for exploration samples is finishing or across the mineralization. Across the mineralization is the NQ size range. In some deposits, you could go down to BQ as well. But as Colin explained, the construction of the hole, you start with a bigger diameter at the top, typically would be an HQ size. And you then narrow down through casings to the desired end size across the mineralization. Where it comes to PQ size, that's typically used for metallurgy test work, because it's the size and the weight of size required for some of those tests. You need a bigger volume of sample, and that's typically even more expensive and more time consuming. Triple tube type drilling is the one that Colin was referring to, that has a third tube inside the drill string. Slightly reduces the sample you'll retrieve, but it improves your recovery of core. This is typically used in the geotechnical assessments to understand the stability either of the pit or the shaft, whatever you're dealing with. This schematic is based on true data from one of the sites I managed, and the line is basically showing a cost profile on what the expenditures would have looked like. And this is to show that the activities and what I've already touched on in understanding your context, your regional geological setting, the mineral systems at play, is a time-consuming exercise as well, and it's an important exercise to set up your drilling strategy and generating a target. But when it comes to cost management, once you start putting a drill rig on the ground, your costs significantly increase. And this is to highlight the importance of being aware on cost management and contract management principles, because that cost escalation needs to lead to a return on investment, which is in the production space. And I've separated in this production into two, because I've found in my experience that most people arrive at the production phase and they convince themselves that all that there is to know about the deposit is final. There is still opportunities that lie in life of mine expansion. In some cases, this could mean low grade ore opportunities. In some instances, it does mean high grade ore mineralization that might not have been known in the mode of occurrence in specific areas. And obviously the cost would then drop off post mining when you've depleted the deposit, and I expect it to be rehabilitating. Critical thing is geology, drilling, and target and mining are always and planning, mine planning at the background. They are always in an iterative process where your current drilling informs your next plan, which informs the next target plans that you need to be putting in place as a geologist. And the key thing is the more you drill, the accurately you drill, you're decreasing risk for the business in terms of recovery. But the important also to note, before the mining exercises, you need to go through critical stage gates. The last one, which is most alludes most geos in my opinion, because it's typically handled by mining engineers. This is the concept stage of a project where the geos focus on data collection, but limit themselves in helping the engineer connect the dots. The engineers focus typically on the best way of extracting the deposit, but the way and the interpretation of the deposit is always a conversation that needs to be guided by the geologist. And never forget the minerals systems that are at play. Remember, I spoke about the ligand and the source, the plumbing, the trap, and the fluid escape pathways. Those four critical elements generally are always at play. And please do not forget those things, because they inform the processes that drive that iteration between target generation, exploration, mine expansion discussions. And that's a space where geologists needs to be driving the conversation and supporting business, critical business decisions. Now, we can move over to the drilling QA/QC methods. When it comes to drilling QA/QC methods, this is the fundamental piece of work that the geo needs to satisfy themselves. They have understood the process of drilling, the extraction, the packing and storage of their core samples before the logging starts. And if the samples were not ruined or compromised during the drilling stage, the next stage that the samples get compromised in is in getting them out of the drill site to where the logging happens. In most instances, and the environment allowing, I generally prefer preliminary logging being done on site. Reasons for this is a hard lesson I learned as a very young geologist, where I a lot of core boxes while transporting them, and obviously things fell out of the box. Had I not listened to my then boss and mentor now of having a preliminary log with photographs on site, I wouldn't have known how to piece together those core boxes that fell over completely. It was 3 core boxes dealing with a total of about 21 meters that were compromised in the middle of the borehole. And the fact that I had photographic evidence of what it looked like on site before we even picked it up in the preliminary log, and obviously the markings that I'll talk to in the next sessions, do not underestimate the criticality of that part. However, it is not always possible, which then leads us to the criticality of making sure you also plan to how you're going to move your core samples from where the drilling is happening to where the logging will be happening, because those could be easily kilometers apart, often uneven and rough terrains that you need to travel with the core. However, the primary focus or the initial steps of QAQC include what is referred to as a directional survey. To explain this, we're going to have an engineering exercise, and the question really here is, what is the connection between the pivot in the neck of a dove and the concept of directional drilling? The importance of that stability is basically how, as the hole progresses with depth, as a geo or doing the directional survey, you know your position in space, and it's an XYZ location. And remember, one of the things that Colin touched on is being accurate on depth. And this is one critical component of that depth accuracy. What it is about is a gyroscopic method. There are other methods of doing this, but typically preferred method lately is a gyroscopic method, where the propagation of a hole is basically set up by a gyroscope which maintains a rotor and a spin axis and a gimbal, which remain fixed relative to the movement of the hole. And as the probe goes down the hole, it records at whatever intervals is set, every second, every 10 seconds, or every minute, whatever the set intervals, its position in space. And it's always reading its location or its position in space relative to the angles between the 3 components of the gyroscope. And this is a critical thing to understand, because what it leads to is that even if you're drilling a borehole and you say you're drilling at a vertical hole, it's never a true vertical hole. There is rotation or deviation from the planned hole. And typically you get this in terms, either in a graphic representation from whoever did the work for you, or they'll give you a CSV file that tells you the borehole number, where it was drilled, and then gives you the direction and the depth of the borehole. And as you can see here, the hole was planned for vertical, but it's not exactly -90. It changes, and those millimetric differences are quite important. In some instances, it can shift up to 10 degrees. So it's very important to know that propagation with relative depth of your gyro survey, because that shows you the path of the drill hole. And obviously, as a geologist, you need to know this and correct for it in your interpretation at a later stage. In some instances, you want, as a geo, and this is typical of precious metals like gold and platinum, where you want to drill a particular hole and you intersect the main mineralization, then pull out to above where your mineralization is and intentionally force your drill string to deviate. And this is basically something referred to as deflections. It's more cost effective than going back all the way up to surface and drilling another hole 10 meters away. And you would have your original hole as the mother hole. And then when you're done with that and you understand all your mineralization and testing, you go out and you drill all these splays in as many directions as practically possible. And that piece of information helps in the accurate modeling of what you're going to be dealing with as a survey. As a geologist post the logging, the critical aspect here is your accuracy of your deflection surveys, because you need to know exactly in which direction that hole you planted, in which direction did it actually go. The next phase, which touches on QQC methods, is what is referred to as core recovery. The critical part in this conversation is knowing what was drilled or what the drill advance was versus what was recovered from the hole. So in typical exercises where your drill string is 3 meters, or rather your drill rod is 3 meters, your drill string advances 3 meters at a time. However, that does not suggest or mean that the core inside your barrel is 3 meters. It's always going to be around 3 meters, give or take, let's say 5 centimeters in what I've gotten used to, but you can't assume that number. So it's where the first part of the conversation is the total core recovery, abbreviated in here as TCR. If you remember what I said, these are preferred being done, and it's best being done at the drill site, if at all possible. And with drill contractors that are investing in making sure they deliver quality samples, they would normally do this as well. And your duty as a geologist is to verify that part, not to do the entire core recovery in the string, but to accurately verify that and spot check that it's been done correctly. What it is the total length of core that was recovered with each drill run. In this example here, the recovery was 2.98. Then the next part that becomes useful in understanding, and also preferably at the drill site, is the solid core. Now, what this is typically core that is fully cylindrical and solid, and on average 2 to 2.5 times the diameter of the core you're drilling with. And the importance of understanding the solid core is how much of the core is affected by structures, joints, and veins, and broken horizons underground, and what other portions of the core are actually competent pieces of core. The relationship between total core recovery and the solid leads to the conversation of what is a rock quality designation, which is summarized as an RQD. And this is typically expressed as a percentage, and it gives an indication of the competence of the rock you're dealing with. So the higher your fracture frequency and all of those things, the less meterage you'll get in your solid core, which means it reduces your RQD. And this is where the conversation with geotech engineering starts. However, it's not a purely geotech conversation. It gives you as a geo an understanding of the set of structures that you need to pay attention to. The higher your RQD, the better your recovery is. And obviously in your drill and blast exercise, you will also have a solid or a relatively better drilling versus a lower RQD environment where most of your blast energy will escape through the fractures. So that's typically what you as a geo need to be psyching yourself to understand. In this example here, RQD is roughly 69%. And it's mainly driven by areas where you have intense fracturing and breakage. However, you need to always consider that natural breaks do not affect your RQD in instances where the solid core was broken. Artificial breaks was broken by a driller to allow it to fit in a box. It's natural breaks that you want to take into consideration. At this point, it's my opportunity to drink water. We're going to do a quick exercise. One of the questions that was asked in the previous talk was, how do you know as a geologist what the depth is? Colin explained this. Let's see if we explained, or rather the explanation stuck. The exercise that we're going to be doing is basically an assessment of what the drill should be. The answer is already given there. You can calculate yourselves and satisfy yourself that it is that depth. After this slide, Tanya, we can take a 5-minute break just to recuperate, and then we'll continue with the rest of the discussion. However, what I want to highlight on this page is that the approach you can satisfy yourself, and most of the QAQC on site I was referring to is a layout of this fashion. This is a form I implemented in one of my campaigns, where this information you typically would write there, and the drillers can normally assist with some of it. But obviously the confidence of all of this, the onus is on the geologist. The information is just about the drilling itself. What was the whole number, which rig drilled it, on what date, the method, the start and the end of the date, and the date in which it was delivered wherever the logging happens. The core barrel and the hammer is the attachments of the drill string at the bottom that Colin explained. The quill rod is the rod that the rotation unit is in contact with, and it's typically always above surface. So when you're referring to stick up, it's typically a portion of the quill rod that is above the surface. Odd rods are rods that are an odd length. It's not the standard length. So in this example, the standard length and the quill rod is 3 meters, and there are no odd rods, so that's why it's 0. Then the total is basically a total of everything in the drill string, and the stick up is the portion of the drill string that stays above surface. The next thing I just want to highlight is this 10-point quality and safety or sheet checks. And you can set up these as yes or no answers, and this helps the total site management as a geologist, where you're not only looking at the safety stuff, you're looking at the environmental stuff, you're looking at the people elements in terms of their health and hygiene, and obviously all the other procedural matters that the actual drilling exercise needs to be governed with. At the bottom, I speak of a chain of custody to always know who handled the samples and how it was handled between the drilling and the logging. Because in this, as I've already explained, the next opportunity after drilling to compromise the quality of the core is in the transport portion. And after the transport portion, it's on the portion of preparing for logging, which is taking it from wherever it was stored, putting it and laying it out for the geologist to log, or you as a geologist laying it out for yourself. So that's that. At the bottom, and this helps for me with part of connecting the dots as you go along and piecing the dots, is a quick yes or no answer and an estimate of thickness if you've encountered mineralization. And this for me has been a useful tip exercise, where sometimes the person who's funding and expecting the results from the exploration is not on the site, could be in a head office or across the continents in another part of the world where they want to know how the campaign is going, and randomly you'll get a call to say, what did you encounter any ore in the previous however many boreholes you've drilled already? And knowing and having this yes or no answer and that number there, it's not for you to think of on top of your head, but to give a rough estimate of what you're dealing with, and keep a structured way of managing the data, because by the stage you get a call, you might not even have gotten the opportunity to log in. So recording that piece of information up front actually helps with those conversations, so that you keep your stakeholders, especially the financiers of the campaign, in where the exploration budget exercise, because it is very expensive. So that's me for this slide. The next slide, Tanya, is just a short 5-minute break, but I'll leave this one on to allow people just to satisfy themselves. You can put in the chat box if after the break, if you get to a different number.
Masi, there's a question in the chat. If you could share the formula for the depth calculation.
Tanya, I can type the formula, but I really prefer that people don't know the formula, rather they understand the relationship, because what Colin was explaining, it's just an arithmetic exercise. So the process of getting there is understanding the engineering design behind a drill string. So what we have,
okay. And to cause that is your answer. You have to work it out, as opposed to just getting a formula.
See, Ntokozo has worked it out. I hope you got the same number. I have gotten someone giving me a different answer before. Interesting getting to understand how they got to the answer, but we finally convinced each other that that is the correct one. The head is down. Before we move on, there's a question. Considering the unintended deflections, what is the best way of picking up structure, angles, and less contacts? Would you advise that they be taken from the core axis and work it out mathematically on a spreadsheet? We'll touch on part of this conversation at a later stage, but I think the critical thing in doing that is first understanding how much is the deviation. Then you can use the deviation and the coaxis relative to the planes you'll be measuring. In other areas where the competence of what you're drilling through allows, you can do downhole surveys other than deflection surveys. And I think Nolene will touch on this in the subsequent talk, that lead to your structural logging information and how orientating some of your core is a useful exercise. So the core axis is typically useful if the core is orientated and that being done correctly. So look out subsequent part of the program. There was a question, but it was sent privately to me by Kulumango's question. Just touch on it, is related to the one I just answered, but it goes more the direction of correcting it and the cost implications of it. Kulumango, it's twofold, the answer to that question. One is being aware of it and correcting it in the data interpretation and modeling phase, where you do not assume that the borehole would have been a -90 or a minus whatever the angle you drilled, but you actually use the computer program to correct for that, because you would house the deviation data in your database that you can correct for it. And what it means is that you adjust the blend azimuth with the actual data you get from a deflection survey. If it is absolutely important that the hole propagates in a specific direction to a specific azimuth and plunge, what then becomes is the frequency of your deflection survey. And there are mechanical ways of trying to correct for the direction, but that obviously has cost implications and time consuming as well. So what becomes important in that space is understanding what your contract arrangement with the drilling contractor or service provider is, to be actually able to factor that in, because if it is not part of the contract, that additional work is going to cost the contractor, and they're not going to be the happiest people to do it, because it's typically not their fault that there's a deviation. That's typically something that relates to how the site is set up and how you place the rig, plus the rocks you're going to be drilling with. So here, varying hardness and structures influence the propagation of your drill string in 3D space. There's a question from Dogozo about the odd rod. Dogozo, if the odd rod was an additional rod, yes. Sometimes the odd rod is, the rod count could remain 67, for example, in the rod string, but you find that not all the rods in that structure are 3 meters. This is very rare these days, and it's typically very low cost exploration exercises where rods are either hard to find or very expensive for the drill contractor and the company that's contracted them to do the exploration, where they would agree that they can use odd rods, but then you as a geo need to know they are in use and measure all of them and separate them from their normal length. Safe, you might want to satisfy yourself. You might have to satisfy yourself by measuring each and every single rod. That exercise is a very time-consuming exercise, and it just tells me that there's little trust between you and your service provider. And one of the important things here, you need to build trust, that your driller and your team will tell you that, look, we used so many odd rods, there they are, these are the standard rods. You can just do a normal count on the standard rods and measure the lengths of the odd rods. Okay, if we can then move on. Now we come to the fun part of logging. What the aim of logging really is, ultimately delineating an ore body. And when you begin this exercise, always have the end in mind and iteratively refine your targets. And by target here now is not defining a new deposit, but in which area of the deposit it's most important to drill to get to the quickest possible answer to the economics of the deposit, and maintain a working mineralization estimate. This goes back to the comment I made in the depth check form, where you'd keep a rough log of which boreholes intersected ore and a rough estimate, because that allows you to do a matchbox exercise of estimating what volume you're dealing with and possible tons if you know the volume density relationships already. And if you've seen the chemical assays from the lab, you then attach grade to that rough calculation. And obviously the reporting guidelines are quite important, knowing are you in the early stages of exploration where you're dealing with exploration results, or you are in a more advanced stage where you're dealing with an indicated and measured resource. What you see in this exercise on the bottom right is exactly what I'm alluding to in terms of refining your targets, where you see that everywhere it shows the reddish color, which is an indicator of mineralization, is consistent with everywhere we've already drilled. So in this understanding is to say that initially, before that understanding with a geologist getting involved in the pit layout design, the assumption was made was the pit layout is in that area, but you can see that drilling with purpose does highlight that the pit layout was only based on existing geology. But when you go back and you understand the modality of occurrence and the mineral systems at play, you can find that the pit layout is actually limiting the size of the pit. And key here is in areas inside the pit layout that were also not drilled, there is no mineralization being factored in here. And this is one of the telltale signs for me that the ore interpretation is influenced and it's slightly biased by where drilling has occurred. Where there's no drilling having occurred, there's no information. So your exercise as a geo is to be fully aware to how this conversation is unfolding post the drilling and logging, so that you do not add to the situation by narrowly focusing on areas that you think that's where the deposit is, but understanding the ore body mineralization. And this area is actually an environmentally sensitive area as well. Most of the areas that are not being drilled are these whitish blue colors, which are basically wetland sensitive areas, and only allowed to drill in those areas in dry seasons. And a photo of an area as such is behind the vehicle. There is a river, and there are rules and laws that allow when can you drill within a certain distance of protected areas. And being aware of these things as a geos, you then plan your drilling in such that in periods where you expect to be dealing with a rainy season, you are outside those buffer environments and you communicate as such to the mine design people that are using the information as it comes in. Because if they put this into a mine planning and they schedule it out and they report that, they might either misrepresent the deposit, and you might be adding to that by not communicating some of these details. The principle, I think, next for me, logging, that if you cannot measure it, you cannot prove it. And the key thing here is that logging as an exercise is a science, and it's not a subjective interpretation of what you're dealing with. You need to be putting measurable observations to the rock properties. You can't be using general terms that the rock you're dealing with is gray. What do you mean gray? And this, I've seen it happens a lot. And it's not specific on the size of the company or at what stage of the exploration exercise, but the value of being specific to measurable properties means at a later stage you can quantify deviations. The intended outcome of this is good accuracy and precision, but sometimes this can be difficult. But at the very least, if there's compromise on accuracy, do not lose the precision, because if the rock is gray and the mineralization rock is also gray and you're dealing with a precious metal, generally it will be very difficult to see the mineralization by your eyes, but being specific on what type of gray and other properties you're dealing with in a mineralization zone helps distinguish between a Merensky reef and a bastard reef. Which is a barren and unmineralized version of the other. And at the very least, if your description is on point and the rest of the measurable properties are on point, you could be out, yes, on description or rather interpretation, but at least your description will help the next person to say, no, look, what Masi meant here might be this, and goes back into the archives and the data to verify a possible alternative to what you've logged. But what you can encounter, especially where the value is based on time, the quality is compromised, and what you find between geos, especially where you have more than 3 geos on a site, you'll find that the description of the same thing is not consistent. And this for me is a problematic space to find yourself, because in this exercise, it means what I describe as a particular mineralization, somebody else describes it differently. What helps in this part of the conversation is the ability to peer review each other's logs. And recent history and exploration, we were quite strict on this, that we do not capture and close any borehole in the main database without at least passing it to one colleague to have a look at what was described. And this is also a learning and coaching exercise, because you get to listen to your colleagues, and this is both ways, seniority and Julia, to say what informs the thinking behind the logging and the description, and it's where the power of continuous learning sits. The next exercise of the logging is obviously data capturing in a database. This slide in this section is just in here to highlight the fact that you are the geologist, not the database. The database is just here to store your information, and it's governed by CQL, typically, not geology language. So always think about how the database needs to capture and register the information as you log, and be detailed. I have found and met geos that are skeptical about writing comments in their logs, whether it's a paper log or it's a database log. Please go the extra mile of writing a comment, because like I say, if your accuracy is out but you're precise, or at least you are detailed enough, it enables somebody else to review and assist in aligning the descriptions to a common description. And bear in mind the GEO, which is used a lot in the computer science space. You put in bad quality data, you'll get a bad quality data at the end, and you basically garbage in, garbage out. Not having a database on site or wherever the logging is happening, it's not the end of the world. You could be as detailed as you get on a simple Excel spreadsheet or paper log, where you at least the critical part about the rock itself, the information of the textures and the structures and the mineralization, and obviously, as I've said, comments. Do not write a PhD thesis in your comments, but at least the specifics of what you're observing. And this is the space where that not necessarily interpret what you're seeing, but putting in all those details that inform an interpretation, so that at a later stage where an interpretation is required, there's enough detail in your logging process to describe what you were observing. Because typically what happens in big companies is that the geologist logging is not always the geologist that would be building the resource model and the estimations. So that information needs to filter through the entire geology value chain estimation. Now, coming to probably the section which is probably my most favorite in the logging, defining the parameters of that highlight the science behind logging. And it's basically a conversation based on what could be referred to as parametric consideration, meaning it's a quality-based, measurable or quantifiable properties. The starting part of the conversation is borehole and project data. The hole has an ID or a number, it's a unique number. The project has a name. The geologist logging has a name, and this is to know who to blame when things are not right. I'm kidding. This is for making sure that you can follow up if it's somebody else. The driller information is important to be able to do the accounting in terms of the chain of custody. It's not to say who's a better driller than who. The start and the end date, some projects run over years. So you want to know at what phase of the project that particular hole potentially falls, because it could also explain to you at a later stage what was the frame of mind within which the drilling was being done. And then obviously critical from to depth, where did the hole start? to what end. And the survey data, very important. Where on surface of the earth is that borehole? That's what it's about. And three fundamental components there is what spheroid you're working with, the coordinate system at play, the X, Y, Z elements of that coordinate system, please. Typically what you find in most boreholes is the X, Y. It doesn't tell you the Z. The Z is important in the space. That's your elevation above sea level. And then the accuracy, is your survey a meter accurate or is it 10 meters accurate? That information is fundamentally important. In this image here is an image of a borehole I worked on in Eastern Bushveld, and that's roughly in the eastern side of the country. That borehole is an ID I still remember to this day. And if you can read, you can actually see it on the concrete as well. It's a C and a H and a 6. So the borehole is CH6. CH is the farm name, farm parcel or survey parcel within which the drill was made, and 6 is the 6th hole in that area. Everything else then gets referenced to H6 as a mother data entry point in the database. The next part of the logging is the actual geology, starting with the lithology. Name the rock, please. Be specific about the name of the rock. Don't say a pyroxenite. What type of a pyroxenite? The contacts, traditional can be simplistic, and always look out for the contact in as great a detail as possible. Weathering, you'll find and you come across a lot of weathering data that says low, none, high, medium. Please put a number. Even if you are wrong, it's not 2%. At least you gave an estimated number. And if you are consistent, it can be quantifiable at a later stage, because sometimes the amount of weathering is indicative of geotechnical occurrence and stabilities you'll be dealing with. But if you're not putting a number to it, you're not informing the processes that follow the exploration campaign. And remember, the exercise and the intention here is to log with an end in mind, because somebody needs to use the data to do something. You want to offer them as much data as possible at the later stage. Alteration, this talks to being accurate about what the type of alteration, not the high, low, medium, or not, that can happen. Alteration, in this case, let's say ceratization, that tells you you're identifying specific set of alteration minerals that are observable, either by hand or microscope, or whatever the case is, or hand lens, whatever you would have been able to describe as a geo. And if you're not sure what type of alteration it is, that's not the end of the world, because this would always relate on the original rock forming minerals. So understanding what the rock forming minerals is, there's only a limited number of alteration possibilities you could be dealing with. But being able to be accurate about its ceratization, it's a different evolution history versus being general. You can't be guiding. Color. I know all of us are taught those 12 colors that you get in a box of crayons that we use when we draw our sections. But there are means of actually putting a number to color. The one I prefer and I've used in the past is the Mansell system, which looks at the hue, the value, and the chroma. The hue talks to the differences, what distinguishes one color from another. The value is basically an indication of how light or dark that hue is. And the chroma is the strength, what other people link to brightness of that color. So being able to put a number to that is basically useful for a later stage, not dealing with 50 shades of gray. Texture, again, specifics, massive. Sometimes I see a lot descriptors that say massive, but on second look, and please cut the core if you're not sure, a portion of the core, make it wet, put a little bit of water to just help your eye, because logging a dry core, you might miss those details, even at a millimeter scale. Those differences are quite important. Structural geology, do not forget your fractures, patterns, frequency, and the fill. And this leads back to the discussion around doing your total core recovery and your solid core recovery on site. Because if you know and you have a good handle of what it was on site, and you're doing this now after logging, you can see very well where you might have induced fractures through transport, and you would not now capture those as part of your logging description. Somebody asked about the core axis. It's best if your core is oriented, but that's not to say do not capture that angle. The angle is fundamentally important, because with the angle and the deflection survey corrections in the model, you can know how your deposit is sitting in 3D space at the very least. And stratigraphy always tie back to your field setting, in which regional local geology and what outcrops and river cuttings are in the vicinity. And if not, there's always a mine. If it's a brownfield exercise, what does that intersection in the core look like in the pit, in the mine, or in the underground surface cutting and development? So always keep the field setting in mind. Contact, just to illustrate a point, the description here would have been in the initial log, it's a conformable or a sharp contact. Upon review, you actually realize that it is a shared contact, because all the telltale signs of sharing, like slicken sides and slicken lines and foliation, are there. The angles on either side of the contact are not consistent, and in this area, the geology is well understood. What you see, at the top, what you've encountered, the edge is one thing. At the bottom, the edge is another, and the material between the contacts is the same age as the bottom part, and it shows that the only way this happens in a vertical hole is if material is either sheared off or folded. So this informs that this is not a natural break, it's an unconformity of sorts. And already at this stage, you've built a picture that you've just drilled through an unconformity. You've left the previous stratigraphic horizon, gone through a zone into the next, and your understanding of that transition and that zone is fundamentally important in terms of modeling and visualizing how your mineralization and your deposit is sitting. It relates to the stratigraphy. As I said, one part is the older part in the previous image. That part is missing, and that part is caught up in between the unconformities, and that portion there is at the bottom of the hole. And what all this now links to is that you're dealing with a real unconformity where the middle section here is squeezed at the top of the older stuff, and younger material is squeezed between two older successions of the same stratigraphic horizon. Back to the massive textures to illustrate the same point. In the core, and because it's a relatively fresh drill, you do not see, and the eye cannot see and perceive that this is a micro-layered succession. And again, the field settings is important. And what's become important here is also the modal occurrences, and that's where the variation actually lies. And seeing that these are a specific needle type minerals, they have a preferred orientation of lying, and that defines the thin laminations that you see in the field. But in the core, naked eye doesn't see it, and you would have to make the core wet at the very least in some sections, like that piece of core there and in that section. If it's wet, you can actually see the micro laminations in it instead of describing the rock as massive. And I have a comment I normally tell geos that I mentor and reporting to me that massive is a boring description of rocks. Next aspect is the mineralogy discussion. Basics, know your ore forming minerals, not only the crystal structures and the abundances, but the chemical formula behind it. This is the start of understanding the limitations of chemical assays, because if your chemical assays don't match your understanding of your ore forming minerals, you have a starting point where you could be either dealing with a change in a genetic model or a quality assurance and a quality control issue that relates to your lab. Either answer is useful in ensuring the integrity of your data. The next set of minerals, and Tanya typically disagrees to this, is that I don't refer typically to gangue, I refer to other minerals. But Tanya would say there's diamonds and everything else. So in the case of diamonds, perhaps you might need to consult Tanya, but in my space, I prefer describing them as other minerals. And the reason behind this is that even though I know they're gangue minerals, is describing them as gangue typically places a block in the thinking process where you would think that it's a discard and it's going to go to waste in any case. But the importance sometimes is lying in the fact that alterations don't occur on the ore forming minerals or changes in a genetic model in a form of alteration or whatever happen first on the so-called gangue minerals or other minerals. And obviously where the mineralogy is too thin or too fine to see, what becomes useful is having access to even petrography and the mode of occurrence and being able to tell, and allow yourself to make time and insist on having at least one thin section or block made of your ore. It might be tricky sometimes to remember the operation of a microscope, but it's a fundamentally important exercise. One of the examples I recall is dealing with the same ore, different deposit, and certain things structurally did not make sense, and not giving up led to an opportunity where thin sections of the ore and some of the rocks, the hanging and footwalls of the deposit, we made thin sections of these, and seeing some of the primary and altered minerals and the reactions between the two actually helped make sense of the structures and what we could be dealing with, because those minerals would only occur under specific conditions. And it helps narrow down what the geology you're dealing with. And as it stands, there's a couple of research programs that are running, trying to make sense of an alternative interpretation of that particular deposit, knowing that the microscopic and petrographic data that we found from there is a deviation from the accepted genetic model in the area. So pay attention to that level of detail as well, because the answer is not always in the core, at least from the eyes, but in the core in the form of using microscopes and hand lenses to that level of degree as well. Sometimes in other areas, this might not be in the scope of an exploration geologist, but at least know who and where in the company or in the contract base of the exploration project you could shift samples like that to someone who can provide the service to you, either an external company or finding a research person at a university or a consultant, whatever the answer to the question is, but do not leave unanswered questions. What came out on one of these exercises, and this is now data that's been being gathered through mineral liberation analysis, and what you'd see is what we typically would define the rock as one mineral. You would see there's at least a 20% of something else, other minerals or gangue in the ore itself, and these are fundamentally important in understanding what the beneficiation impact will be. And if this detail is not well understood, could sit very well with an issue where the ore behaves in ways in beneficiation and post-beneficiation use, like case steel making, where the disintegration of the ore in a furnace to make steel is actually related to that 20% of the mineralogy. What's in that 20%, not the 80% which makes up the bulk of your ore, and not understanding that 20%, or at least how much the other minerals are intertwined with the ore, is limiting the conversation, and you could prevent the opportunity of being upfront and proactive in managing and using the ore body to receive the best possible revenue out of it. And I typically say to stakeholders here is that the ore body dictates what can be done, and the ore body will always offer the information that is needed. We just need to apply ourselves in that fashion, and understanding that the best possible margins are linked to the best possible use of the ore body. And the other minerals, or the typical gang, is never a less important exercise, because there could be hefty penalties associated with getting that balance wrong. And I'm talking in the tune of millions of US dollar penalties. Your analytical data, what did you send to the lab, and what did the lab tell you the analysis are? This is where your sample ID and your description of your sample is important, and the quality assurance that goes with it. And here and there, you want to have reference material and blank samples. Some blank samples, the samples the lab doesn't know what it is, or which sample it is related to. Reference material, it's got a set and a known chemical value. And the importance of those two is basically telling you as a geo how accurate and how good your lab. This data is typically the data that most geo accept as it is. Please do not always accept what the lab. There could be a fundamental mistake in the management, the handling of the samples. And I'm not to say labs are not accurate. It could be that in your sampling processes, there's a sample swap, and it could be in the transport, then there's a misplacement of a sample. It could very well be in the lab as well. But being aware and able to trace the steps back to the core is always going to be useful in linking a sample to a piece of core that comes from a specific X, Y, and Z location on the surface of the Earth. And again, those properties are measurable. If you have the opportunity to also your physics, and this is typically very important for deposits where you find that measuring and orientating core and measuring structures is a fundamentally difficult exercise because of either the complexity and the structural terrain you're dealing with. Downhole geophysics becomes a very useful tool. So there are things like relative density that you could run probes for. However, the guidance I always give is do not run a density probe without a porosity probe, because the higher your porosity on the same mineral or rock, your density will be relatively lower. And the important aspect of those two relationships is it's a cross-check of each other. So a porosity probe can help you infer density, and a density probe can help you estimate porosity, but one measures the other. So that relationship for me is always important. If one of your probes is out, the relationship and the inference will always be a huge deviation, and you can put a number what's acceptable as a difference between the two. So basically, what can you accept as a inferred density from a porosity probe versus the technique you use to actually measure the density itself. Televiewers, depending on, again, what you're dealing with, televiewers basically help you visualize the in situ in the hole. There's other methods like radio properties or microwave properties of the rock, which talk to the aspects of the rock that you cannot see. So there's a technique like RIM that's in use in other places. And obviously what also becomes very useful is UCS. UCS is uniaxial compressive strength. How hard is the strength, is the rock you're dealing with? This is a fundamentally important piece of data with the televiewers in designing and helping drill and blast conversations, because the hardness of a rock and the fracture frequency that sits in that rock enables you to see what the potential energy leaks and the end for that the drill and blast design needs to account for. Because what you want to retrieve at the end of the day in the mining phase is the most optimal fragmentation of your rock to enable the most optimal load and haul exercise. And obviously when it gets to a plant, there's crushing and beneficiation processes that would rely on the initial fragmentation of a rock. So that UCS is very important, and you can get that information from downhole geophysics. Which then brings us to probably the most favorite part of mine when it comes to exploration and even geology. It's not just collecting the data. My first rule, and as best as possible in one of my flip charts, I will have a working section. What that means is that in a select section line, whether I drilled and logged that borehole as a geologist or not, I will know what the next holes on either side of my drill holes, what they look like, and a rough sketch of the geology going down on each hole. Keep that working, and as you drill, you fill in the gaps. And what that leads to is already getting your head to think about that end in mind, to say this thing I'm logging is a deposit, and I'm trying to maximize the data that leads to the economic economic recovery of the ore body, and all of that will always be dependent on the primary data and the quality thereof that we connected, and be curious and test the genetic model. In an area about, let's say, 25 kilometers away from this one deposit, the drilling just didn't fit. And as you can see, the surface I drew here by hand was a relatively flat surface. In the area that I'm dealing with is no longer flat, but the depth to ore was not conforming to the expected regional depth to ore. And we were surprisingly in and out of ore quicker than I would have expected. And in terms of then unpacking what's happening in that area and the changes in topography, realize that I can't be satisfied that I've intersected the ore and I'm back now in the waste, the footwall, stop the drilling and move on. Being curious, as Colin said, is have a nice conversation with the driller to say, I know in this particular area, or in general, we typically drill to this particular depth. What I need us to do is push on for so many other meters and be crystal clear on what is in the contract for that conversation. The longer you keep a driller unnecessarily in a drill site, they won't be happy if they're not seeing the economic advantage of it. And this is where you as a geologist need to understand that, yes, the driller wants to give you a quality sample, but they are also interested in maximizing the value of doing the actual drilling. So having closed up that discussion, we drilled another week or two in that site and found and came into the realization actually the ore duplicates more than once. So the ore horizon is not one. Had we stopped the whole shot, we would have missed multiple ore horizons in a particular location. And that was a fundamental discovery in also understanding that genetic models change and structural geology aspects influence the relationship between the local and the regional. Not ever take that part and our understanding ever for granted. And the working section line helps in seeing where things are not gelling and you cannot explain them in the simplest possible form. Without that working section line, you would miss opportunities of curiosity and expanding the ore. As you can see there's a portion where the ore suddenly becomes deep, and you don't need to be 100% correct in terms of why it's that deep. Safe to say that you can show it that in this area there's an anomalous thickness in the ore, and understanding where that anomalous thickness on the ore is important, but equally understanding why it is there, because then that refines your targeting and it iterates back to the next areas you want to drill. Same section presented in different forms, and the key part of this discussion for me is that always look at the validation of what the database captures as part of your log. Always go back and zoom in and out of the core and check that the description and what you saw in the core and the photos that you captured and how it's appearing in the borehole is as representative of what you saw, being aware of the lithological and stratigraphic relationships, because once you move on from this conversation and you say you've done your part, the next person dealing with that piece of information and all that data can misinterpret what your eyes, and there's no replacement yet for the eyes of the geologist at the primary contact with the core. And also be able to zoom in into what are the shortcomings on your drill management. So for example, in this cross section, I just highlight a few issues where the first one is obviously the logging is inconsistent. Suddenly the purple layer disappears because the way these holes were logged is different from those ones. The second issue is that in some instances, the log is very simplistic, and all of a sudden you've got these thick packages that are not well described, and the detail that is captured elsewhere, you cannot do anything with it in other portions of the same section line. And the only thing you're left with is a guesstimation of how the lithologies are connected. In some instances, the holes are stopped way too shallow, and it forces a particular interpretation that might not be fitting, versus whether that some of these holes could have been drilled deeper. And as you can see, some of the things terminate in shorter spaces than they could, simply because that the holes that could help piece the information do not extend deep enough. So never drill a hole to chase an end depth. Always drill a hole to chase the end of your mineralization. And if your footwall and hanging wall and all the structures that you see as the drill hole develops are not convincing you that you've hit the end depth or the end zone, then it would be, the onus would be on you as a geologist to inform whoever is governing or managing the project to say, in this particular location, I do not feel satisfied that we've reached the end of the exercise because of ABC rules. And reasons that are linked to the stratigraphy, the physics, the geophysics, the structural geology, and all other data sets that you'll have at your disposal. Because at this stage, when a person is now modeling the deposit, it's fundamentally late to integrate that information back, because they will use the information that they had at their disposal. And remember, I said garbage in, garbage out. And the end in mind is always going to be mining. And not just mining, the most cost-effective way of extracting the deposit, and it's about doing the right work upfront and doing it once. And the key thing here in this portion of the mine is just highlighting where, in some of the areas, you can see that the pit terminates right on ore. Terminates right on ore, which shows that there could be expansion opportunities, and limited geology information did not offer the mining engineers enough information to build a mine extension envelope to that side of the pit. And remember, always work with the reasonable prospects of eventual economic extraction. Now, what that means is there are certain descriptors that are used in the mining space, things like strip ratio and all those NPVs, IRRs that are being used. Those are indicators of the cost of extraction, but they tell you nothing about the margins. The conversation must always be, what would be the margin? And for me, to get to do that exercise, always be curious of what is the resource shell, where does the resource end versus where did we say the pit will end? Because that difference is always where you want to operate in, and always look into the conversations around what is the pit layout if you would assume double your revenue. Because what that means is inside the double pit revenue shell, you would avoid as best as possible to putting permanent infrastructure, because the cost of removing that infrastructure at a later stage when the economies of scale change and it becomes economic to mine those areas, you would have to do double work of, first of all, removing the previous infrastructure, then mining. And in fact, it's probably 3 times, because you have to now find a new place of putting that infrastructure again. So that's where the cost escalations go out of control, and limiting your scope as a geologist in that conversation, you're creating a situation where you are not guiding the conversation again. And the conversation must always be such that the deposit must dictate. It cannot be my interpretation as a geologist that limits what the deposit must be, and it cannot be what the mine design finds. Yes, of course, there are those areas where it's risky from a safety perspective to do certain things, but important is what is the resource development plan and what is the life of asset, and why those conversations, that's where the stage gates and the double pit revenues sit in. And it's probably a talk on its own, that one with somebody else, perhaps, to go into those details, because that's where now the resource estimations and geostatistics and mine design become fundamental, and mine design, strategic mine design at that, become fundamental conversation, because in this space, the focus is to giving and front end loading the geology exercise ahead of all of those discussions. That brings me basically to the end of what you need to know as a geologist. Thank you for having me again. Always enjoy this part of the exercise, Tanya. I'm happy to take questions.
Hi, Mercy. Thank you so much for that presentation. Okay, there's a question on, excuse me, on the chat. At what intervals do you prefer logging? Or do you just look for changes? Also, do you have minimum and maximum intervals for ore and non-ore?
Very important question. I developed a methodology where the first thing before I look at the interval is go look for those changes, especially unconformities, if they are, just mark them out. And I'm always guided in that by the smallest change my eye can see into that level of detail. And obviously the important answer also you need to balance that out is what timeframes do you have? And this is where logging as a pair or having a peer review is important, where one of you could easily be putting in the major unconformities and somebody else within those strat packages or lithology packages goes and puts in the fundamental changes within the same package of rock. And that's for me, they're always well-structured approach, because first of all, you are framing yourself in a clear understanding what rocks can be correlated with other rocks in the next boreholes, and then your eyes tuned into those fundamental changes within the same package. Those fundamental changes is what informs your complete understanding of your genetic model. In terms of the ore waste discussion, remember, especially in the overburden and the hanging walls, in some deposits, it might even be parts of your footwall. It takes the same energy to move your ore and your waste, just different destinations. So always operate with the fundamental that you will have to understand your waste. And this is probably touching on the conversation of changing the psyche from grade control in the mining space to ore control, because all rocks can be attached to cost or value. And the value of waste sometimes is not giving you money, but it's saving you money in the sense that you could very well answer a question of the necessity of double handling or moving waste that otherwise you wouldn't know had you not paid the attention to the waste. So always treat all the rocks with the same level of detail they need. And obviously the sampling and the budget will control which horizon you use as a sampling interval, but at least in your description being consistent, because you are mindful that a deposit is not a deposit disconnected from its surrounding or its environmental context.
There's another question. Can you re-drill areas that were previously drilled where the end of hole was at a shallower depth?
Yes, it's possible. Not always, but it is possible. The info or the data that are critically important to making that decision is knowing your previous drilling. And you recall where I was talking about what I call the survey data about the borehole. Who drilled it? When was it drilled? Who was the driller? You'll know what the method of drilling was. So if, for example, the previous drilling was a percussion drilling and the hole was kept, so it means that there's a likelihood that the top portion still has casing. And before making that decision, you want to know, is the hole open from top to bottom? And that might take you a day's worth of an exercise to test that. And if your current driller, if it's a different one from the previous one, understanding that you're asking them to set up on an existing site, there will probably be contractual and cost discussions on that and risk discussion more than anything on that. And you can then further that borehole deeper, conditions allowing. Another way of targeting that is twin drilling. What that means is that there is an allowable distance from the previous hole based on your survey method accuracy, that within a certain distance from the previous hole, the hole can still be considered the same location. You just put an alphabet or something at the end to say it's the later version. So the original hole can be something like CH6, the second hole, which is a twin hole, CH6A. So that's another way of doing it, but obviously that has cost implications, as long as you know what the depth you need to drill past is, and obviously the end of your mineralization as well, what you're targeting. So you can always do that option as well.
Thanks, Masi. Matumi makes a comment. Great presentation, Masi. Working section lines help determine the direction of the main channel in a river system, as indicated on your connecting the dots slide. And I can just add to that, very, very definitely. The idea of creating working section lines is something that I absolutely believe in as well.
Spot on, Tanya. I have no words to add there. It's a very spot on comment, and please make the time as best as possible. And this is probably for me the most fun part of being a geologist, with a glass of wine in the evening.
Yes, the glass of wine definitely does help to lubricate the little brain cells.
Yeah, definitely.
Are there any questions for Masi? Okay,
Crossing my toes
thank you once again, Masi, for your time and expertise. We will definitely call upon you same time next year.
IMDEX in a nutshell. I don't know how many of you are familiar with IMDEX. So we just going to go one slide back. So we are actually the two previous companies, AMC and Reflex, that was bought over by IMDEX. And we are a drilling optimization, rock and real-time subsurface solutions company. So the two legs of the companies are the AMC, drilling optimization, includes the drilling chemicals and the muds. And then we have the Reflex part of the company, which is the core business that I think most geos are familiar with, and that's the core orientation tools and the downhole survey tools. So we operate right around the world. We're an Australian-based company, so it's Australian headquarters, but we operate across all regions: North America, South America, Africa, and Asia Pac. And yeah, so we're located right around the country. We have offices in Joburg, so we have a manufacturing facility and our tools offices in Joburg. So if anyone wants to come and have a tour, you know, just pop me a mail. I'll share my email address in the chat afterwards, if that's fine. And then we have another regional office in Ghana. So what do Reflex do? So I think at the core of our business is not just providing data to our clients, but providing quality data with strict chains of custodies and as real time as you get. So it goes from our drilling optimization, creating the best possible core for geos to collect data from, to our rock knowledge sensors, from our Sprint, I think is the Sprint easy tracks and the sprints, and the downhole surveys and the rig aligner tools that most of familiar with. And then the area that I actually find most interesting, and that I'm also from a geo, is our real-time data software, which the core is our Hub IQ. So that's where all our data goes from our different instruments. From a single hole, you just have all your data in one place, and it's QA/QC. Then yeah, it's available at your fingertips and integrates with some of our software, like our geochem software, like iGas, and also some third-party software, and then yeah, to get you to those answer products. So if you have to sum it up maybe in just a few slides, then you can see that the IMDEX Hub IQ is actually the center of IMDEX. So that is at the moment still for free for clients, and that just collects all your data from your MUD to your IQ logger structural data, through to some of the in-field geoanalysis equipment and hardware we have. So that's just a more detailed summary of exactly what we do. So it's from the drilling optimization. You can see at the bottom, it's all the fluids and the muds and the mud engineer and the real-time data on your controlling your drilling fluids. And then the core business right here at the right bottom of the slide is our survey tools, some geophysics easy gamma, rig alignment tools, and all of that just seamlessly integrates into the hub for single holes. Then we have some our structural IQ logger. I think a lot of geos are familiar with that one. And then in-field geoanalysis, we have XRF Connect software, which actually you can couple with a PXRF unit. And yeah, that's just another slide showing all our tools and how they actually integrate into a hub. And then on the right-hand side, we actually integrate with third-party software such as Leapfrog and Acquire, and then seamlessly with our iGas geochemical software. And then we have a few new interesting products like AI Siris, which is an artificial intelligence software that actually interprets your spectral data that you can upload into the app as well.
Thanks very much for the opportunity to do this talk. I know I was joking just now about being thrown under the bus and doing it again next year, but I do think it's a very important part of what an exploration and a mining geologist needs to know. So I first put this talk together when I was working for Reflex, which is one of the companies that Valerie has just spoken about. And what we were trying to do was to get the geologists to take more control of the drilling part of their exploration projects. And I'm going to start and say, guys, listen to what Colin said and Massey said. be curious, go out to your drill rig, ask questions, understand what the drillers are doing, understand that they know what they're doing, because this is a very, very important part of exploration, and we'll get to that in a second. But this talk isn't just about structural logging, because you know, everything that goes into the drilling is involved in getting good structural readings. So a downhole survey isn't just a downhole survey, and a core orientation isn't a standalone process. So I want to go through the different processes that make up getting good structural logging. Righty, so there we go. So this is what I'm going to be talking about during this presentation. Why is structural logging so important? And then how you're going to get your structural information, best practices to generate quality readings, and then also, you know, what to look out for, what areas to look out for, and how to mitigate them. Okay, so let's start with why structural information is so important. So Massey has touched on it, and one of the most important things, obviously, is we're drilling and we don't understand what is underground, which is why we're drilling. And by understanding your structural logging and your structure underground, you are going to understand what you're going to find when you start with your mining. So it also predicts where your mineralization is, because as we know, a lot of the structures form pods where your mineralization is accumulated and concentrated. So if you can identify the important structures in a project, you can obviously predict where your mineralization will occur. Then once your mine is being developed, you'll know the structure, which will determine the design of the mine, how your ore blocks are going to perform while you're mining. And then again, also environmental concerns. So your geologists, your hydrogeologists need to understand the structural geology, because they are sites of groundwater flow and penetration, which may affect the leakage of toxic materials from your waste dumps or salty water leaking into your aquifers. And, you know, the East Rand is a perfect example of this. So let's start with how you are going to get your structural information. So as I said, it's not standalone processes, and it's obviously not just what you can see on surface. So one of the most important things to understand is where your ore body, where your core and where your rock is in 3D. So it's very important to survey your collar position to know exactly where you start drilling, and then a downhole survey to determine the dip and the dip direction of where you have drilled your hole. And then obviously you also want to understand in which orientation your rock is before you take it out of the ground. So that is why it's so important to orientate your core. If you drill it and break it off and pull it out, and you have no idea in which orientation it was before you pulled it out, it's useless. You know, you will never understand the structure underground. Okay, so that is basically how you start. But there are also other things you can do to ensure that your final structural measurements, which is where we're going to end up with this talk, are as accurate as you can get. So as Vernick mentioned, you can optimize your drilling to get the best possible core. And Colin did say, so the best recovery and less breakage and loss. Then you're going to survey the holes with tools, and you're going to choose the best tools that you and your company can afford for this. So you ideally want to choose something where your results can be viewed immediately and also remotely, and your hole can be resurveyed if it's obvious that it's deviated too much. So, you know, you can always, like, then if you need to, re-drill your hole. But you know, at worst case scenario, that is re-drill, but you will know where your hole has gone. And also it's very important to have a secure audit trail. So I'm afraid that sometimes the drillers do give you what you want, and if they see that there is like a huge deviation in your survey, they might actually fiddle the results. So a lot of times in the field, our drillers have brought us our survey information on bits of paper, on Excel spreadsheets, and all of those you actually really can't 100% trust that what you're getting is correct. So you're looking for something with a really secure audit trail. And then you're going to ensure that your orientation of your core is done correctly, that the core marking is done correctly, and only at that point do you actually start doing your structural logging. So you can see that structural logging contains many elements that are pulled together, and every step of the way must be done as accurately as possible. So if your survey is slightly out, and then the orientation is slightly off, and the core mark isn't done as accurately as carefully as you can, and then the geologist is a little sloppy with the structural measurements, you can imagine that by this point you've got quite big errors in your final structural results. So I think my most important message of this talk is do everything as carefully as you can, because as Masi did say, you know, your name is on that logging sheet and you're going to be held accountable. But if every geologist takes control of their part of the work, you're going to have a fantastic product. And when they start planning the mine, those geologists can trust the information that you are giving them. And then the other point I would really like to make is you have to know what's happening at the rig. So when I was working with Reflex, this is my favorite story. I went out to site one day and the geologists were complaining about the Reflex tools, the core orientation tools. And they were saying, no, they don't work. And they want to return them. So I said, okay, fine. So let's just go down to the rig. And the geologist said, oh, no, don't worry. The driller can bring the tools back up to the office, which was admittedly a lovely air-conned container. It was lovely and cool, and outside was just sweltering. So now the driller brought the beautiful Reflex survey tool. I opened the box and it had never been used. It was brand spanking new. So I asked the driller what they were using to do the core orientation, and they said that they were using a spear. My point of the story is the geologist did not know this. The geologist had not been to the rig once in 5 months. So go to the rig, ask questions, understand what's happening on your project. Okay, enough lecturing. Let's carry on. So we've gone through this already. It's obviously more than just taking the measurement on the drill core. And I've gone through the fact that you've got to ensure that your survey, your orientation, and your logging tools are fit for purpose. So a lot of times, cost is the definitive factor in what tools you use. But do try use the best tools that you can. Ensure that your drillers and your geologists are properly trained and supervised. A lot of times, you as a geologist have no control over who your drilling company is, but you can make sure that they are correctly trained in the tools that they are using. And everybody takes ownership of their part to give you a quality solution. Have your QA/QC systems in place and do them every day. Don't wait until the end of your project and go, all right, let's check the QA/QC, and realize that your survey tools weren't working correctly and your surveys are all incorrect. So good structural quality data is only as good as the drillers and the geologists' care factor, the accuracy of the drill hole surveys, the measurements, and then of course the follow through. So you're going to find some challenges. Obviously, not everything goes perfectly. And these are things that you should be watching out for, again, all the way through the process. So in drilling, your core can rotate when breaking, and this is going to affect your orientation of the core. And you're going to obviously sometimes find that your core is totally broken up or totally ground to like powder almost. And obviously you can't orientate that core. Downhole surveying, inaccurate surveys. And yeah, again, don't trust anything that you get, and check everything. In orientation, so orientating the core as well as making the orientation mark, both of these can give you errors. Drawing the orientation line from the mark, that can also be errors. And then in logging, incorrect measurements and data transfer. So a lot of times in exploration projects, there are more than one geologist working on the project. So a lot of times you're looking at other people's work. Be aware that these problems could occur, and make sure that you understand what is happening on your core. Righty, so let's start with the downhole surveys. Colin likes to say that there are certain things that are absolutely definitive in life. One are that you pay taxes, the second one is that you die, and the third one is that all drill holes will deviate from their planned path. This is so true. Deviations can be significant, so survey your holes. Let's have a look. So here is a mine plan, open pit, as well as underground over there. The holes have been assumed to be undeviated, straight, and from your mineralization in each hole, your ore body has been drawn in. So the pit's been designed around where you think your ore body is going to be, as well as your underground infrastructure. But if your hole has been surveyed and it now looks like this, this is where your ore body is now interpreted to be. And you can see that it actually goes into the pit wall. Your open cast pit has been designed in the wrong, has been created in the wrong place. Your underground infrastructure is never going to hit your mineralization. So you're now got your stoping waste, and you're going to have to do more underground development. It's going to be dollars and dollars and dollars, and your reputation is shot. So that is the importance of surveying your holes. And it's not just the modeling that's important. Over here, you can see that the faults are steeper than expected. The mine was developed, and you now have a huge failure in your open cast pit. Right, so you get different survey instruments. A lot of them are quite old, but let's have a look at how you survey your holes. They are separated into two different groups. Your magnetic instruments can be used for non-magnetic environments. So that is your normal drilling, and there is going to be no magnetic interference in that at all. These instruments are divided into two groups as well, the mechanical and the digital. So we don't really use mechanical survey instruments anymore, but you might end up in a project where they have used them. You have like older geologists who have not yet moved into the 21st century. So it's just good to know that those did exist. And then you have your digital tools. And then the other group are your non-magnetic instruments. And these are used for when you are expecting magnetic interference in your ground. Again, these are separated into two groups. And I will explain this in more detail. So you have your reference and your non-reference instruments. So let's have a look at these. So these are the old mechanical ones, right? I've never seen them, not even on any of the projects I've worked on. If you do have any questions about them, Collins the person to ask. So you can see there, you know, they're fragile, they're not auditable. There's no built QA/QC. Manual data entries, which is another problem where mistakes can occur. So all of these are, for me, that just looks like really bad stuff and like, you know, hard to use. And I think that's why most people obviously have moved on to the non-mechanical and the digital instruments. So obviously, because I worked for Reflex, I understand those tools better. And you might find this like a little bit of a reflex bias talk. So what we're looking at now are the magnetic survey instruments. As I said, these are the ones used when you're not expecting any magnetic interference. And all the digital tools are robust, solid state electronics. They can do multiple survey shots so that they go quicker and you have more accurate information. So, you know, the more shots you do downhole, the more accurate your information is going to be. There is a built-in QA/QC functionality. It's auditable, digital data capture and transfer, and then the data is easy to interpret. So all of these things, as I said earlier, are so important in making sure that your survey information is trusted. So here we're looking at instruments like the Reflex Easy Track, the Bort Longyear True Shot, and the non-magnetic ones are made from non-magnetic material, but they do need aluminium spacer rods with the drilling to keep the instrument away from the magnetic tools. They use magnetometers to determine the magnetic field, and then accelerometers determine the direction. And they can't provide an azimuth with magnetic ground inside of drill rods or near man-made magnetic items. So these are the cheaper option when you're looking at digital survey tools. And as I said, you know, if you're not expecting any magnetic interference, they do a great job. If you are going to be drilling through magnetic ground, so your BIFs, massive peritite, etc., you would then start looking at your non-magnetic instruments. So these are divided into the two. On the left, you can see it's either referenced or non-referenced, and the only difference really is that for the reference instruments, you put in the position, and the non-reference tools are north-seeking, and you only have to put in the azimuth. There's obviously more benefits to using your non-reference instruments, but that does add quite a lot of cost. So again, it's very important to choose the correct tools that will do the job you're looking for, and still, you know, be cost effective. It's always very important because ultimately everybody's trying to make money. So these non-magnetic survey tools aren't affected by magnetic ground or drill rods. They're very robust. They can be used inside all types of drill rods. They're intuitive, they're easy to use, and again, the built-in QA/QC report generation. And yeah, we're looking at like the Reflex gyro. So the non-reference one, this is the one I said you only have to put in the latitude, and they are north-seeking. This is the Reflex Sprint. It's the latest Reflex, although Vanik might correct me, there might be a newer one. All measurements reference the geographic north, no alignment required, and historically, this is where you would have got service providers to come out and do your surveys. So one of the good things about using these kind of survey tools is that they are operated by drillers and they are done while you're drilling your holes. So historically, you would drill all your holes for your project, and then you would get a surveyor in to come and do your downhole surveys. So, you know, the downfall of this is that by the time your surveyors arrive, after, you know, drilling 40 holes, half your holes might have collapsed. So your surveyor couldn't get his tools down to do the surveys. And then also you've now drilled 40 holes and you have no idea whether they are accurate, whether they've deviated, and you haven't been able to interpret your project while you're busy drilling. So, you know, as we saw with Massey, it's like it's every night you should be looking at your drilling data, putting it into your interpretation so that you are building your project in your mind as you go along, and you can then make adjustments with your drilling, where you're going to do your next hole, as well as when to stop and, you know, when to carry on drilling. So to get back to these tools, you can survey both RC and DD holes, diamond holes. That can be done on vertical as well as angled holes. Okay, so there are other, sorry, I just want to get to where we are, that are, again, older technology, relatively cheap, but there are quite a lot of downfall to using them. So even though we don't use them very often, I just wanted to include this slide so that you are aware that, you know, these things are around. So when you're busy doing your surveys, some issues that you need to be looking at, when you start getting your surveys back and they just look dodgy, you know, do a conformance check on the tool. But when you rent these tools, the service provider should give you very good training on how to use them, how the drillers must use them, and how to make sure that they are working correctly. If they don't, get a new tool. But if you have checked the tool and the tool passes the check, then go and have a chat to the drillers to make sure that they know what they're doing. Don't wait till the end of your project. Really, you need to continuously check all the steps of your surveys to make sure that you're getting the best results you can. Okay, so now you've surveyed your hole, you have your survey information back, you know where your hole has gone, you know how it's deviated. Hopefully you have got mineralization, and if you haven't, well, that's got nothing to do with the survey or the core orientation. So let's move on to see how you're going to orientate your core. As I said earlier, so core orientation is the process of determining the in situ orientation of the drill core in the ground. You really need to make sure that you understand how your core was situated, because if you pull it up, and also, you know, if you don't orientate your core and you pull it up and you don't know how it was situated, you really can't use it to understand your structure. And then the drill core is marked to reference either the gravimetric bottom or top of the core, and we'll go through that in a second, in inclined holes or true north direction in vertical holes. Okay, as I said, errors in the position of the orientation mark will impact the accuracy of your structural readings. It will then impact on your geological and your model. It will impact on the mine design, and ultimately it's going to impact on how much money your company makes. So the core orientation tools, there are two different methods and two different kinds of tools. The first are the contact or front end instruments, and then the second lot are your non-contact or back end instruments. Again, the first one, your front end instruments, are quite old. They're non-digital. We tend not to use them anymore, but because they are cheaper, and again, you might end up on an exploration project where you have, you know, the more experienced older geologists who actually have been using them for their entire lives, and they just feel that why change them. So especially the spear, you might still encounter a spear. Oh, thanks, Colin, for this slide. So the front end ones, they obviously go onto the front end of your drilling. So they actually make a mark at the bottom of the hole before you start drilling. Sorry, so the bottom of the hole, which will then end up being the top of your core when you pull it out, which means that it has been marked in situ before you've even drilled that core. Okay. So the key considerations would be that, sorry, I've lost track of myself here. When you are choosing your tools, these are the key considerations. The accuracy and reliability of your in situ rock orientation data, the cost, interruptions in drilling, the production rate, the difficulty in use, and the condition of rock mass. So these are the things you look at before you choose your orientation tools. Right, so these are the front end ones I was talking about. You might still find the spears. And then this over here is your impression barrel. It goes into the front of your drill string, and it hits the rock, and these little pins get moved so that it shows the impression of your rock. So when you pull out your core, you can then reorientate it and put in your mark. I've actually never seen it used, but you might. The advantages of using these is that the orientation is made at the start of the run. So therefore, it's not going to be affected by rod torque and core spinning in the tube, and it is simple and easy to operate. The disadvantages is that you can't use it in soft or broken ground. And then it's restricted to inclined holes between 30 and 75 degrees because it's obviously got to go slide down the hole. You can't use it for upwardly inclined holes. And you do need your operator to be very careful to get a quality mark. It's susceptible to tool damage, and it's slow. So the tools have to be separately run before a new core run commences. Then if we look at your sorry, I've got this thing across the top of my screen, so I can't really see what my slides say. The non-contact or the back end instruments, these attach to the end of your core barrel and they orientate the core tube. So the core is locked in the lifter case and it's brought up. The tube is retrieved and rotated to its correct position, and then the orientation is marked on the core. So there are, again, two different kinds, either the mechanical ones as well as the electronic ones. So the mechanical ones, you're looking at, again, older technology, the Reflex Easy Ori. I don't even think that they sell them anymore. But again, you might find them on a project. It uses a steel ball, marks the bottom of the hole on the soft metal disc. And as I said, it's superseded by electronic systems. The electronic systems, you're looking at things like the Reflex Act 3. It uses a series of accelerometers to determine the gravimetric bottom of the core tube. The operating parameter data is digitally captured, and then it can be analyzed to ensure that the tool is being operated correctly and it's within the design parameters. The advantages of using these electronic instruments is that it's more reliable in soft and broken ground. You have your digital QA/QC data capture. You can orientate it up and down holes to within 5 degrees of true vertical, and the orientation is accurate to 1 to 3 degrees. You can't orientate vertical holes, and it may be affected by rod torque and core spinning in the tube. That can be mitigated by ensuring that the drillers are careful, that they ensure that the rod has stopped spinning before they break the core. So yes, that's where we go. Look for core spin, and then, you know, we're geologists, so you use your geological features across the core to align your core if you do actually have core spin. Okay, so now that you have your orientation, you need to make the orientation mark. And this is where it becomes more the geologist's problem, or where we can ensure more quality in your core orientation. Because up to now, you know, it's pretty much been the drillers that have had control of what you're getting. So from here onwards, it's the geologist. So once you have your core lined up at your drill rig, you need to make the orientation mark. So again, these are reflex tools. You've got your jig that you put your core on, you align your jig, and then you can draw your mark. This one is a little bit more involved. It goes over the front of your core. You align it with your core orientation tool, and you'll see that you can then put your pencil in there and make the mark. So you want to make your mark as accurately and as straight as possible. And if you're not holding your jig perpendicular, then your line is going to be slightly skew. And you'll see when you then draw your line across the top of your core, you could actually be doing it in the wrong direction. Very important, make sure that if you have decided that your line is going to be on the bottom of your core, make sure it's always on the bottom of the core and not on the top. So bad orientation marks. You'll see over here, big fat mark. You don't actually know where the center of that mark is and where you will then draw your orientation line. That one, it's not even on the bottom of the core. So those are from spears. You can have bouncing spears, and you can like end up with 3 marks as the spear has bounced across your core. And then you have to believe that sometimes drillers are going to give you what they think you want. So, you know, they're just going to make a mark anyway. And then it's just something that you need to look out for. When you draw your orientation line from the mark at the on the circle of your core, use an angle iron rather than a ruler. It's longer, and then you don't have to try and line up your ruler. Yeah, you can see over here, you know, this core line was drawn before the core was fitted together. And then over here, it was just totally skew. And then they fitted the core together and realized that they had made a mistake. So other things that you need to look out for, you can't propagate your orientation line through broken core if you can't rejoin it. And rotating your core 180 degrees, you're going to end up with your line on the wrong side. Also, then make sure that you're doing your arrows in the correct direction, downhole rather than uphole. So after all of that, we can actually now start doing some structural logging. I was going to say, are there any questions? But let's just carry on. You can ask the questions at the end. So making the structural measurements is a routine part of logging drill core, as Mati said. And I'm not going to go through, you know, what you log. He's already gone through it. But I can say from experience, for me, it was probably always the worst, most boring part of logging core. I really never enjoyed it. I always handed it over to anybody else that was willing to take it. And in hindsight, I think it is one of the most important parts of your exploration project. And by giving it to, young, inexperienced people, it's probably not the best thing to do. And because a lot of people don't like it, they leave it right to the end. And sometimes, data is not used for months or years later, and we then just assume that it's accurate. And then a lot of the times we start using the structural information. It doesn't make sense, and it has to be discarded, or you have to relog it if you have the core. And if the core is not available, you might actually end up having to drill more holes. So it really is important to do correct structural logging. Righty, so there are many ways of doing structural logging and using it. You've got your manual tools. So those include the rocket launcher, which I actually never thought anybody ever used. And then I was in this huge, big mine in the DRC, one of the biggest mines in Africa, the biggest gold mines in Africa. And all their structure was done with a rocket launcher. So I was flabbergasted, because it is so slow and so time consuming, but it is really used a lot still. Then you have your goniometers, your chronometers, and your core protractors. We now do have digital tools that make the logging much easier and quicker, like the Reflex IQ logger, core photo analysis systems, as well as televiewers. So the rocket launcher, it is actually, although it's time consuming, it's really good because your orientated core is positioned exactly as it was in situ. So you can see, you can visually see how it was, and you can visually see and understand your structures in your core. So you put it in your rocket launcher, so it goes in there. And then the geologist directly measures the dip and the dip direction using a compass and a clinometer. And there are many, many different styles. I mean, some of them are handmade, some of them are engineered. There are many different ones. As I said, you can see it visually, and your measurements are done in situ. There's no conversion of alpha or beta angles required, because you're not using the internal angles. The disadvantages, it is susceptible to setup errors. It's easy to knock, and then it's not accurate anymore. It will pick up the magnetic interference from surroundings and rocks because you're using a compass. The frames can be heavy and bulky, and you can have measurement errors. It's also quite hard to hold a plane against the core and align the compass and the Kleiner ruler on it. So, and again, it's slow and it's a manual process. The other ones that we use, they measure the orientation of a feature relative to the core axis and the orientation line. So you would measure your alpha angle, which is the acute angle between the plane and the core axis, and then your beta angle, which is angle between the orientation line and the lower end of the ellipse. You then use these angles to calculate your dip and dip direction. And generally that will be calculated in a separate software package. You can also measure the plunge and the plunge direction of a line on a plane, and that means that you need to measure your gamma angle. Please be aware that there are different conventions for these angles. So for example, the IQ logger that Vanek spoke about, your angle is measured from the orientation line to the first intercept of the lineation, or the angle can be measured clockwise in a plane from the long axis of the ellipse, or it can be measured from the orientation line to the bottom intercept of the lineation. Just be aware that there are different conventions, and if you have many geologists working on a project or many generations of the same project, you might come back to the same project 5 years later, that you are totally aware of what convention has been used previously. Because if you start using a different convention, obviously you understand that your core orientation measurements are going to be totally different, and it's going to be quite hard to understand where the problems have occurred. So this is another tool that you can use, the goniometer. They're available in different sizes. You measure your alpha and your beta angles. It's quite easy to do. And it's also quite accurate. So your beta angle is up to about 2 degrees and your alpha angle up to about 5 degrees. These are really easy to use. So you align the core with the orientation line pointing down the hole against the 0 on the beta angle. You measure your beta angle on the bottom of the ellipse. And for your alpha angle, you align it to the side of the feature and you just read off your angle. So your sources of error where you're going to find problems is the thickness marker line. So if you have a very thick line, you can see already here you've got a 5 to 6 degree error. And it's going to give you 1.5 to 2% measurement error. And you're going to find throughout all your orientation, if you use a thick pen, you're going to give yourself errors. So try and use the thinnest pen you can. Another source of error could be the uncertainty in the position of the apex of the ellipse. And this is going to be particularly at your high alpha angles. But it's not just the goniometer that's going to give you this error. This is something that no matter what tool you use, if you're not certain where the position of the apex is, it is going to give you an error. So what I used to do is just draw where I have made my measurements. So if somebody comes back later, they can see what I have measured or what my team of geologists has measured. And then again, you've got to be quite careful that you're measuring the top of the ellipse rather than the bottom, because that is going to give you a 180 degree beta angle error. Low alpha angles can be difficult to measure, and there's an estimation. So you'll see that your angles are in increments of 5 degrees. So you are going to be averaging up to 5 or down 5. Parallax of errors. So hold it up to your eyes so you can minimize that. And then you need to use the correct goniometer or chronometer size. If your core doesn't fit into the tool, you are going to get wrong readings. So chronometers, very similar to goniometers, again, available in a variety of sizes. They measure the alpha and the beta angles. Again, increments of 5 degrees. And with a chronometer, your apex of the ellipse is aligned with the 0 beta mark and the angle read at the orientation line intersection. Please be aware that this is the reverse of the goniometer. So if you're using goniometers and chronometers on the same project, then you need to be really, really careful that the geologists are using them correctly and aligning the core in the correct way. So we've already gone through the sizes and using a thick marker, and then please ensure that you are using the core pointing in the correct direction when you fit it into your chronometer. Righty, so these look quite old, and I always think, well, we never use them, but actually people still use them quite a lot. So you have your core protractors, and there are different ways of measuring your alpha and your beta angles. Just be aware that you're reading the correct end of the ellipse, and again, the position of the apex. And ensure that you're using the correct diameter. So with all the tools, just ensure that you use the correct tool, the correct size, and you know which way your core is pointing. The wraparound core protractors, I think a lot of people still use these. So you wrap it around your core, you read off your alpha angle, making sure that your protractor is orientated facing down the orientation line, and then you read off your alpha and your beta angles. I can say that they're not very waterproof because you print them on plastic. So I have found that crying at the core yard isn't really helpful to your protractor. And then the mistakes, you could have it upside down. So it does help to have the side up stick on the correct side. And because you print it, make sure that your scales, that you're not scaled it so that it is printing correctly. And again, use your correct size. So I honestly think that this is the best thing since sliced bread. It takes away all the pain of all those errors that I have just been talking about. It is digital. It has an app that calculates your alpha, your beta, your gamma angles, and gives you your dip and dip direction immediately. So you don't have to do it. There's much less chance of making errors. You can visualize the readings on a stereo net. So while you're busy doing your structural readings, you can already build up a picture of what your structure looks like. And it automatically syncs, or excuse the spelling there, to a cloud-based hub. So this is what Vernig was talking about earlier. And if you haven't seen one yet, or you haven't used one yet, give him a ring. It does take the pain of structural logging away. Obviously, like with any other tool, there are some sources of error, but not as much. You just have to make sure that you properly align the IQ logger on the orientation line before zeroing. Make sure that once you have orientated the IQ logger, you don't move the core. And then again, like the other tools, the low alpha angles are more difficult to measure. You can measure your structure on the side of your ellipse rather than on the apex. It's less accurate, but it is still possible. So for example, if you have half core and your apex has been cut off, you can still take a structural reading. It's really nice because you actually don't have to pick up your core in order to do your structural readings. And yeah, you know, it's just a lovely tool. So if you're interested, get hold of Vernig for that. Then there are other ways of doing your structural readings, as Matthias mentioned earlier. You can use things like, you know, the Scan IT from UCP, StereoCore, Photolog, and you have software that uses core photography, and then you draw the lines and points on structures. You know, you don't have to be on site to be able to do this. The downfall is though that you're only seeing one side of your core. You can't pick it up, and you know, as geologists, we all do like to lick our core, so you won't be able to do that. And you can obviously make your measurements at any time. It doesn't have to be when you're in the core yard. And because you have great photos, core degradation is less of an issue. As I said, you only see the one side of the core. Poor image quality and resolution of core photos will be a problem. And then again, your parallax and lens distortion. Subtle structures may be difficult to see. And if you're working on a structural project where that is very important, then you're probably not going to be wanting to use that as your method. And then televiewers, Massey went through that. So, you know, there are the two different varieties. You have your optical and your acoustic. And you can map the structures in RC holes, and you can see zones of poor core recovery or lost core, which is a benefit. It avoids the issues of poorly orientated core, but we're all going to be very careful and make sure that our core is perfectly orientated going forward. And it's generally run by other contractors, so you wouldn't do it yourself, which means that it's expensive and the data turnaround times can be slow. So you have your high resolution optical sensor, and it's going to require your dry hole or clear water, which is sometimes a problem too, and you're going to need a good color contrast. Then acoustic, they use ultrasonic beams to measure variations in acoustic attenuation of the drill hole wall. Your hole has to be filled with fluid, and you have to have a good acoustic contrast. It's very good in identifying subtle fabrics, such as mineral foliations. I'm sorry, identifying subtle fabrics such as mineral foliations can be difficult. And then also there's some difficulty in telling fractures from veins and alterations. And that is the end. So I am now totally open to any questions if I have rushed through anything and you haven't understood anything I've said.
Thank you very much, Nolene. I am once again reminded of the advantages of pitting in shallow alluvial deposits.
Alrighty, so hello everyone. I guess Tanya has introduced me. My name is Andy Siwe. You can also call me Andy Vutuza. I'm currently a technology advisor here at Acquire Technology Solutions. We are basically a data management software and services company. And today I'll just be giving you a brief introduction to drill hole database management. Okay, so I'm just gonna stop my video for now and reshare my screen. Okay, so our speakers today have basically covered a variety of drilling related topics and the types of geological parameters that drilling can give us, right? So these parameters are basically at the core of business decision-making processes for mining companies. But of course, the data has to make sense. It has to give us information. Therefore, it needs to be stored and it needs to be managed and processed for information. So it all starts with the data, okay? Geological data is an extremely valuable strategic asset, which is used to make profitable business decisions based on the quality and the integrity of your data. It is the single source of truth that guides everything you do within the mining value chain. Now, we all understand that geological data forms the basis and it guides the decisions that are made across the mining value chain, right? But in many cases, this data is underestimated. The value of this data is underestimated, especially when you consider how many meters have been drilled, how many samples have been done, and the related costs. Then to add on top of that, there's the amount of time and the manpower that can add on to that cost, basically. So currently, internationally, the average cost of diamond drilling, I mean, Colin can correct me on this, is like it's approximately $200 per meter. So assuming you have drilled, let's say 50,000 meters, you're looking at a cost of 10 million US dollars. Then you add on the manpower costs, which could easily be an additional 50%. So your effective replacement value is in the region of 15 million US dollars. Now, when you look at it from this perspective, geological data is definitely a significant and strategic asset, and it needs to be managed accordingly. Now, to function effectively as an organization, you need information. For example, a library needs a list of borrowers and books which are borrowed. A mining company needs drilling details. Now, information in essence is just data that's represented in a meaningful way, okay? So the same data can be shown in different ways, and it will provide different information to different viewers. An information system, it must be able to store and retrieve data in a way that is meaningful to the user. So at the core of information system, it's data basically, which is then transformed into information according to the user's needs. Now, before we look at the common types of information management systems that are used within geosciences or within the mining industry as a whole, let's discuss what makes a good information management system. So there's a number of informational operations that a management system is capable of, but the core ones are the collection of your information. An information system must be able to store information. It must be able to process that information. It must be able to distribute that information. And most importantly, that information must be accessible. So let's look at the different ways in which data is managed currently. So you have your hard copies, which are stored in basically physical file systems. Now with hard copies, we know that sharing can be a nightmare. You know, you always have to track where you put a certain form. You always have to check who last saw the key to a certain room that, you know, stores your different files. Finding is also a nightmare. There's multiple places to retrieve related information. Usually, you know, at the production side of mining, you would have multiple cabinets where multiple files are being stored. Sometimes the wrong file can be put in the wrong cabinet and you will struggle to find that file just because someone put it in the wrong cabinet. So this obviously introduces the opportunity for data to be lost in the process, okay? Then you have electronic files, such as your Word or Excel. These are better than your hard copy, but sharing is still difficult. There's also the versioning issues where there's multiple copies that may exist of the same Excel file, and also finding it can be quite difficult. Then you come to databases, which are the best of all. In databases, data is organized and it becomes a central repository for all to access. Now, you might be asking yourself, what is a database? So a database can be defined as a structured collection of data that is stored in a computer so that a program can interrogate it to answer queries, okay? Now, the records that are retrieved in answer to your queries, those become your information that can be used to make decisions. And the computer program that is used to manage and query a database is known as a relational database management system. Now, there are many different types of databases. You know, the best database for a specific organization, it depends on how that organization intends to use the data. In geosciences, they commonly use flat file or relational databases. So what is a flat file database? Basically, this is a database that consists of one, usually very large table, okay? Like the one that you see on my screen. Now, in the context of drill holes, commonly data is stored in a single large table, which displays information about that drill hole. This table can have collar data, like what I have on my screen here. It can have downhole survey data, which is what I also have on my table. You can also have your sampling data being added there. You can also have your logging data being added there. So for visualization purposes, one can say this is a superb way of viewing data. But in the scheme of a good geoscientific information management framework, where you need to ensure that your data is secure, your data has integrity, your data is also scalable, meaning you can accommodate your database becoming bigger, this is not an effective way of storing data, okay? Storing data this way can introduce a number of problems. Number one being that there's data redundancy. So there is repetition of your data and there can be duplication of your data. Like in my table here, there is repetition of the collar information for your drill hole. Also, this can introduce storage issues because you keep repeating the same data. You are using up storage space and you're wasting it, okay? Also, there's the issue of not having cascade delete or update. So what this means is if I delete on an Excel spreadsheet that has multiple tabs, if I delete a drill hole on one tab, right, it might still occur in another tab. So there isn't a good error tracking system in this regard. And also the flat table, at some point, it becomes uncontrollable because you will keep adding more fields. For example, if I add my sampling intervals, if I add my lithology intervals, and etc. And this makes finding information even more difficult. So all the problems that I have mentioned in the previous slide can be resolved by dividing our data into multiple tables that are related to each other. And that's where relational databases come in, okay? So a relational database is a database where the data is stored based on its relationship to other data in the same database. So with the relational database, you have related data that is identified and it's placed in relevant tables. And the rule is each set of data should appear only once. So for example here, this is my flat file database, the large table that I had. What a relational database does, basically, it splits the data sets. So you have your caller information going into your whole location table, and then you have your downhole survey information being saved under your whole survey table. And then based on the common fields between those two tables, which in this case is your whole ID and your project code, you can relate the two tables to each other. There is no duplication of data here. There is no repetition of data. There is a relationship between two tables which are related to each other. And this way, if you're looking, for example, for survey information for this whole ID called ABL001, you don't need to sift through a very large table to find that information. You can easily go to that relevant table, which is whole survey in this instance, and get the information related to that drill hole. So with data stored and managed in one location, multiple applications and users can access information. So with a database that's centrally located, it becomes easy for the users and the apps to interact with the data and to query the information they need from it. And what I mean by applications, I'm talking about now your third-party applications, such as your modeling or mine planning applications or GIS applications. Instead of having to export data out of your database and then import it back into those third-party applications, those applications can now directly also interact with the database from the same location as your users also. So this ensures that everyone is accessing this single source of truth, and it also prevents a lot of data handling and corruption by users, okay? So what I've shown you here, basically, it's a client-server architecture. I'm not gonna go into detail about that because this is just the introduction, right? But basically what a client-server architecture does, it allows employees to share information amongst themselves in a quick and efficient way. So the software that manages your database is called a Relational Database Management System, or RDBMS for short, and that is located on the server. In simple terms, an RDBMS is basically, it acts as an interface between your database and its end users or the applications that are trying to communicate with the database. Now, as specialists in the data management field, we've seen a common set of challenges across the board, from exploration to mining production, from single sites to multiple sites. And these include, I'm not going to go into each and every point here. I'm just going to touch on a couple and just have my laser on here. So for the first one is that we see a lot of data being stored in too many places and data being easily lost, basically. So with a dedicated RDBMS, so Relational Database Management System, your database, like I said before, it becomes the only source of truth, meaning everyone is working on the same database and they're all accessing the same data, okay? There's also opportunity for data to get corrupted. So there's opportunity for human error at capture and also during delivery. Now, again, with a dedicated RDBMS, business rules and validation rules can be set at the point of entry, preventing the input of corrupt or incorrect data. For example, you can assure that the same validation codes are being used throughout for lithology data fields. Again, another example, if granite is being inputted as GRA, as your organization, what an RDBMS can ensure is that each geologist always enters GRA and not GRT, for example. So this way, everything that goes into your database, it's always validated. It always has integrity and it's correct. And another thing that we have picked up with, departments that don't have a robust geoscientific information management system is that there's a lot of time wasted reformatting data for analyses, for example, or for reporting. So a good RDBMS should save you that time, the time that you spend on a task. For example, resource geologists, before they model, they would usually, if they don't have a good RDBMS system, they would usually go through multiple Excel spreadsheets, to ensure that the data is in the correct format, that it is validated and it will be allowed into their modeling software. Now, a database management software, it should allow interoperability, meaning that it should be friendly. It should play well with modeling, GIS, and mine planning softwares. So when you take data from a database that's been managed by an RDBMS, it should move into any external third-party systems in a very swift and streamlined manner. So like I said, to save time, I'm not going to go through the rest of the typical data management problems that you may encounter when you lack a robust system. But the takeaway message here is that poor data management can lead to inconsistencies. It can lead to frustration. It can lead to a loss of data, which in turn results in a waste of money and resources and time. Now, a good geoscientific data management system, it should provide you a single source of truth for your data across the organization. It should improve business efficiencies and enable process improvement. And it should also leverage innovation, meaning you should, an organization should be able to move away from logging on hard copies, for example, and do digital capture on mobile devices. And then most importantly, a good geoscientific data management system should minimize operational disruption. It should manage the risk and optimize your workflows and increase your efficiency as a geoscientist. I hope this has been a good introduction on what to expect on next year's workshop about this topic. Thank you guys for lending me your ears, and please do follow us on LinkedIn and sign up for our newsletters. And yeah, you're also more than welcome to reach out directly to me for any more information. Thank you.
Thank you very much, Andy. Does anybody have any questions at this stage for Andy? Looks like you're getting off lightly.
It's fine.
They keep being, okay, go ahead.
Hi, Tanya. Sorry, just one comment. I don't know if Andy put part of that sample database in deliberately, but I don't know if anybody noticed in some of the samples there that Andy had, it was survey data. There was inclination and azimuth data for a borehole. Yes. That just was garbage. It didn't make sense at all. So in other words, what I'm saying is the survey data was obviously wrong. Obviously one's got to be very careful about validating data before you put it into a database, because once it's in there, you believe it's correct, and that data could not be correct. It's clearly is very, very inaccurate. So that's just the point I wanted to make there. Validate before you stick it in.
And that's what an RDBMS can do for you, basically. I think what I was showing though was just, just to demonstrate how the different databases work.
Sure, absolutely, yep. Absolutely.
And thanks again to our sponsors and also to our presenters. Thanks, Colin, Masi, Nolene, Andy.